Hello and welcome. In this video, we shall take a look at what is a cipher algorithm and what is a key. So till now, we have actually been discussing that whenever you need to send your original data, original text, you always encrypt it, and the other end you need to decrypt it. And we also said that you need to use a specific encryption algorithm and then you decrypt using the same algorithm, right? But the question arises, what actually is a cipher algorithm? So it's pretty simple. Always remember there are only two things when you are talking in terms of cryptography. You need to know your algorithm, which is we call the cipher algorithm, and you need to get an understanding of a key. Right. So cipher algorithm is nothing but it's a cryptographic algorithm, which is a mathematical function, which is used to encrypt and decrypt the data. So I think I told you previously as well, the base or the foundation to all these encryption algorithms or cipher algorithms is mathematics. So when we will take a look at different algorithms like RSA algorithm, Diffie-Hellman, elliptical curve, you'll see they are nothing but a set of steps that you need to follow, and these are actually mathematical set of steps, right? So that is what it says, that it is a mathematical function which is used to encrypt and decrypt data. Now, because it's an algorithm, and if going again by the root word algorithm, it's nothing but it's a set of steps or set of rules, we can call it, right? So it is a set of rules or steps that define how the data is transformed into ciphertext, right? So these are the rules that you use to convert, say, plain text into ciphertext, which is called the encrypted text. And then because you have to convert it back into its original form, so you need to use the same algorithm and then bring it back into its original form, but it is used based on the secret key, right? Or the keys that we discussed. But what exactly is the key? Now you might ask, what is a key, right? So a key is a piece of information that is used as input to the cipher algorithm. Very important, guys. So we are talking about algorithm and keys. So algorithm is nothing but your set of steps, set of mathematical steps, and key is nothing but an input to that. Now, if you might imagine, if you can now think that what would actually be an input to a mathematical formula, it would definitely be numbers, right? So normally what we do is we always consider or most of the time consider large prime numbers. So we are not talking prime numbers like taking number 3, number 5 as my keys. They are really, really large prime numbers which are used as keys, right? So it clearly says the key is a piece of information that is used as an input to the cipher algorithm along with the plain text or ciphertext to perform the encryption or decryption process, right? It is a secret value. So as I said, a key, you shouldn't be telling your key. It should be close to your heart. You shouldn't be telling your key to anybody, right? If it is a public-private key pair, public key can be shared, but secret key, here we are talking about the secret key or the private key, that only the sender and the intended recipient should know about that secret key, right? And that's where we looked at a lot of examples where we saw where Joy and Aileen had to talk to each other and they were using a combination of their own public-private key pairs, right? And as we said, it must be kept secure to ensure the security of the communication so that no man in the middle comes or no attacker actually comes in the middle, right? So now you might ask that, okay, what are the best examples? So there are quite a few common examples of a cipher algorithm. These are DSA, SHA-3 with 256, and SHA-1 with DSA. And we will study some of these as well. But for the moment, what we need to understand is when we are talking about cryptography, the two key elements or the two major elements or artifacts for cryptography is a cipher algorithm, and the input that goes to the cipher algorithm is a key, right? Thanks for watching. Hi folks, welcome back. After getting a good understanding of what is a cipher algorithm and what is a key, it's time to take a look at different algorithms, right? So as we studied in cryptography, there is asymmetric encryption and there is symmetric encryption, right? So we'll do the same way. So because we studied symmetric encryption first, So we will talk about various symmetric key algorithms that are available in the market, or that have been available in the market per se. So the key algorithms are DES and AES. So first we will understand what is DES. So DES stand for Data Encryption Standard, right? So Data Encryption Standard is basically a symmetric key algorithm. Very important thing to notice here is it is a symmetric key, right? It is a symmetric key algorithm that was widely used for data protection in 70s and 80s. So I would say one of the first algorithms that actually came in the market and people were quite excited was about DES, because we actually started with more of like a symmetric encryption first. And then later on we decided, okay, symmetric encryption has its own problems because you need to send the key across the wire and you need to share the key. So that's why asymmetric keys came into picture. But to understand, so DES was a symmetric key encryption algorithm. And note that it was actually developed by IBM. So we know the International Business Machines, right? So IBM is a pretty big company. So IBM was the creator, or who was the company who developed in 1970s. And it was actually adopted by the US government as a federal standard. Very important. So this by 1977 it actually became a federal standard, right? And DES uses a 56-bit key, right, to encrypt and decrypt the data in 64-bit blocks. So as we studied, so you have a cipher algorithm, and the input to a cipher algorithm is a key, or as I said, it would be a set of certain prime numbers, a set of numbers. Here the DES used to have 56-bit cipher key, and if you see, we've taken a good example here where it describes how a DES key or DES algorithm works. What it does, it basically generates a lot of permutations and several rounds. Normally it used to take like 16 different rounds of encryption to actually generate a ciphertext, right? So the encryption process involves multiple rounds of substitution and permutation. So if you see, there are multiple rounds of substitution and permutation operations on the input data. So now if you imagine in terms of Caesar cipher, what we studied was very simple, right? We were just moving three places across. Here we are talking about multiple substitutions. Here we are talking about multiple permutations as well. So all we are trying to make is we are trying to make a very complex mathematical formula to actually come up with a strong encryption decryption algorithm, I'd say. So DES was actually known for its simplicity and speed, and it made it very widely adopted for a range of applications, because people, as I said, they got really excited that DES was able to solve a lot of problems for them. And as we know, because it uses symmetric key encryption algorithm, so definitely it was fast, it uses less computational power. But DES brought its own challenges, right? There were numerous occasions when the DES encryption was broken, and so it was discovered to be really vulnerable to brute force attacks. And the problem was related to its small key size. So the scientists or the mathematician realized that 56-bit key size was not good enough to actually achieve a strong encryption. That's why over the period of time, the DES algorithm died down, right? So NIST then came up and said, we really need to stop using DES and we need to come up with more sophisticated encryption algorithms, and that gave birth to AES, and we will study AES in the next video. It is called Advanced Encryption Standard, and it was developed and adopted in 2001. So if you see, it's not been too long since AES has been there. Several, I would say almost more than a decade, I would say. All right. So so the thing to understand here is that DES was really good when it came, but as we know, the hackers are becoming really intelligent over the period of time. So they were able to break these encryptions, algorithms, and that's why NIST clearly said that we shouldn't be using DES, because it was vulnerable due to its small key size, and they came up with AES. And very, very important point, guys, please remember, DES is no longer considered secure, not even secured today, and not recommended. So it is not recommended for use in modern cryptography. Why we are studying DES is just because, as I told you, whenever we are doing a deep dive in a topic, it's always good to know its base. It's always good to know its history. So how AES came into picture, we need to know, because it came from DES, right? So as I said, when DES died, it gave birth to AES, right? So we need to understand that bit, what was DES, why it was being used, what were the problems, why AES came to picture. So yes, so I would say thanks for watching. Now in the next video, we will talk about AES. Cheers. So after taking a look into the DES or data encryption standard, it's time to take a look into AES or the advanced encryption standard. Now, as we already understood that there were a lot of disadvantages, or the DES algorithm was not considered to be too secure. That's why it was decided that the DES algorithm would be discontinued and we need to come up with AES. So again, AES is basically a symmetric key encryption algorithm. Always remember, we are studying symmetric key encryption algorithms first. So first one we studied was DES. The second one is AES. So AES is a symmetric key encryption algorithm, and it was adopted by the US government in 2001. And if I can say that till date, it is actually being used by the US government, which is the AES encryption standard. And as we already discussed, it actually replaced the aging data encryption standard. Now, just like DES, it is actually a block cipher. So block cipher is basically, it encrypts the data in blocks. So if I give you an example, like a 128-bit block cipher will actually bring or use 128 bits of plain text and encrypts it into 128 bits of ciphertext. Now what it does, if you see, it uses several combinations, and it is using 128-bit, then it uses 192-bit, then it uses 256-bit. So the main thing is it uses several combinations of I would say secret key plain text, and it uses multiple rounds as well, as we saw. So multiple rounds of substitution and multiple rounds of permutations. Just again, the aim is to make it a really complex algorithm, so that not any hacker can just go ahead and break our algorithm or break our encrypted data. Right. So it uses a variable length key with options, as we studied, that you can either use 128-bit key. Now you might remember in DES we used to use 56-bit key, right? That was the maximum we used to use. That's why it got discontinued. And if you see AES, it actually starts from 128, goes to 192, and then 256. So normally the recommended say key size is 256-bit keys these days. And the encryption process involves multiple rounds of substitution. As I said, you are having multiple rounds of substitution. You are having different permutations and mixing these operations between the secret key and the plain text, right? You are having multiple rounds of these. So you are, let's say, you're taking a block of plain text, taking the secret key, generating a block cipher, right? Then you again take some part of the plain text or some block of the plain text, apply secret key, get your ciphertext. So it uses that multiple number of times, right? So it uses multiple rounds of substitutions, permutations, and mixing operations on the input data using a combination of secret key and plain text, as we just saw. And yeah, it is considered to be highly secure. And if you ask me today, most of the financial transactions, military communications that are happening actually are utilizing the AES or the advanced encryption standard. And quite important, it is also adopted as a standard by by NIST. What is NIST? So NIST is nothing but the National Institute of Standards and Technology. So NIST would actually tell us that, okay, which are the recommended encryption algorithms, what recommended key size you should be using. So we should always go with the NIST standards. Similar to that, you always know that there are ISO standards. So ISO is nothing but International Organization for Standardization. So the main takeaway is that AES, or the Advanced Encryption Standard, has been adopted as a standard by both these organizations. And quite importantly, if you see, AES is implemented in software and hardware. So a lot of vendors are actually utilizing it. So if I give you an example today, say Oracle. Oracle is a database technology or a database or an RDBMS for its encryption, which is called Transparent Data Encryption, TDE. It also utilizes symmetric key encryption, and they use AES for that, right? So very important, and the key point here is that AES is considered to be the most widely used and secure encryption standard in modern cryptography. When I'm talking about symmetric key encryption, if anybody asks you which is the go-to algorithm in symmetric key encryption, your answer should be AES, or the Advanced Encryption Standard, right? Please remember the DES, or the data encryption standard that we studied. It was just to understand the various algorithms and to understand the death of DES led to the birth of AES. Thanks for watching. Okay, so we started from very simple things. We studied the history of cryptography. We looked at different techniques in cryptography. We looked at say symmetric encryption, asymmetric encryption. We also studied I would say several approved algorithms for symmetric encryption like DES. We studied AES. Now it's time to understand the NIST approved asymmetric algorithms. So I'm actually quite excited to actually go deep dive into all these algorithms. Now, what is NIST? The first question comes, what is NIST? NIST is nothing but it is the National Institute of Standards and Technology. And NIST actually develops cybersecurity standards, guidelines, and best practices and other resources to meet the needs of the US industry, federal agencies, and I would say the broader public, right? So, and NIST has given us a list of approved algorithms, and I would say it's pretty good. Why? Because there are so many algorithms available in the market, and you as a vendor, let's say you are coming up with your own, say a new application, and you need to use encryption in that, or you need to employ encryption in that. So which one to go for, right? So that's why NIST has actually published all these algorithms, and these are the RSA algorithm, which is the Rivest, Shamir, Edelman, and these are actually based on the names of the I would say the mathematicians who actually came up with this algorithm. Then we have the DSA algorithm, which is also called the digital signature algorithm. As the name suggests, it is the algorithm which is used in today's world for making digital signatures, for signing say digital or using digital certificates. Then we have the ECDSA, also called the elliptical curve digital signature algorithm. Another key algorithm that is actually used for digital signatures is ECDSA. Then we have another one, which is the Diffie-Hellman, which is DH algorithm. And so what I want to say here is we will do a deep dive into all these algorithms. We will understand what are the mathematical formulas behind these, what kind of keys we should be using. So it would, honestly guys, it is going to be a really interesting journey from here onwards. So keep watching. Hello folks, welcome back. So the time has finally come to take a look into the various NIST approved asymmetric algorithms. Now, the very first one that we will be working on or taking a look into is the RSA algorithm. I would say RSA is the oldest and the most popular of them all, right? So what exactly is the RSA algorithm? So RSA is actually based on the creators, and to be honest, I would say these are the geniuses in front of you. So they were Rivest, Shamir, Edelman. Now, the thing is that as the name suggests, RSA, so it's actually based on the names of the creators. So Rivest was actually born in 1947. He was a BSc, which is Bachelor of Science in Mathematics at Yale University, Stanford, which is US. Shamir, who was born 1952, was a BSc or Bachelor of Science in Mathematics PhD at Weizmann Institute. So this guy was from Israel. And Edelman, born 1945 and a BA in Mathematics PhD, and he was from California, Berkeley. So again, US. So as you can make out that these are the guys who came up with the RSA public crypto system. And they are not really computer programmers as such. These are actual mathematicians. They are PhDs. If you see the most, like a couple of them, they were actually PhD in maths, right? So this is where I was trying to tell you, when we are talking or understanding crypto system, the base of crypto system or cryptography is mathematics. So if you're really good at mathematics, then you can always work on these kind of algorithms. Right, so moving on, let's try to get a better understanding of what RSA algorithm is all about. So RSA, now we all know, stands for Rivest, Shamir, Edelman, right? Named after its inventors. Good. It is a public key cryptographic algorithm. So I think by now most of the guys can understand when we say public key cryptography, what we mean is that you are using different keys for encryption and decryption. Now you can easily compare it with the symmetric key encryption, where we said in symmetric key encryption, the same key is used for encryption and the same key is used for decryption, right? But RSA algorithm, because it's an asymmetric algorithm, it is using different keys for encryption and decryption. And RSA is actually known for a couple of use cases. So as we said, you can use it for secure communication, and it's also used for digital signatures. Later on, we will see more advanced algorithms like the elliptical curve, ECDSA, I would say, and the Diffie-Hellman, which is actually used for this. But I would say RSA is also used for digital signatures. The main thing is that it relies on the difficulty of factoring large composite numbers into prime factors. So the base for the RSA algorithm is working on prime numbers, and we will see with an example as well that you talk about prime numbers. In our example, we might take smaller prime numbers, but in real world you actually take large, very large prime numbers, right? So the key generation actually involves choosing two large prime numbers, right, as I said, and computing their product. So you always have a public and private key pair. So you will notice that for creating or generating the public key, you would be using the product of these two large prime numbers. So one part of that public key would be a product of these two large prime numbers. Again, we will actually take a good deep dive into the calculations that are involved around this. But for the moment, just think about it, that you are it's based on the difficulty of factoring large composite numbers, and you are, for the key, you are actually choosing two large prime numbers, right? And for the creation of a public key, one of the components is the product of these two prime numbers. And pretty simple, right? So RSA says that you have to raise the plain text message to the power of public key. So in this, we are getting the public key, and here we are utilizing that public key and taking the result modulo. So result modulo is more of like a remainder, right? So when you're doing a division operation, that the modulo is, you can say that the kind of remainder that you're getting out of that division, right? So the RSA encryption involves raising the plain text. So basically, anyways, you are starting with the plain text and you need to convert into a ciphertext, right? So you take your plain text and you raise it to the power of the public key. So you in the first instance, you're getting a public key. So you raise the plain text to the power of public key and take the result modulo, which is taking the remainder. And again, now when you have the encrypted text, you actually get your ciphertext. Now, what does decryption do? So decryption would be input is for the decryption is your ciphertext. So here you work on your ciphertext, you raise the ciphertext to the power of private key, right? And take the result modulo. So same way, right? So it is saying when you are talking about converting plain text to ciphertext, you take plain text raised to the power of public key. And for ciphertext, you take the ciphertext raised to the power of private key. And we will see actually in the example. So don't get confused for the moment. Just try and see and try and understand what are the basics of what happens under the hood. And yes, like any other encryption technology or an algorithm, RSA has been vulnerable to attacks if the key size is too small. So don't ever go for small prime numbers, always go for a large key size. And you know, the NIST has now recommended that you should at least be using 2048 bits. Now you can actually imagine the key size is so important, right? When we talked about the DES algorithm, we were saying that it started 56-bit key, and that's why it was not very secure. Now here with RSA, which is part of the asymmetric algorithm, we are talking about a key size of 2048 bits, which is pretty humongous key size. And RSA is actually slower than other algorithms. As I said, that there have been advancements. Like we are talking about the guys who were born in 1945, in 40s, and I think this algorithm would have been there by 1970s or so, right? But there has always been advancements and new algorithms have come up, like the elliptical curve, Diffie-Hellman. So they offer more stronger security, I would say, and they are rather more complex as well. This is when you are actually trying to understand, it's more easier to understand an RSA algorithm, but when you talk about elliptical curves, it talks about more advanced mathematics. So yes, RSA is slower, but there are other algorithms that have come up. And RSA, even though it's slower or whatever the problems we talked about, but still it's really widely used. So as I told you guys, it's quite popular, very popular algorithm, still being used, still being supported by many systems and software, and it is the popular choice for cryptographic applications. So a lot of applications still utilize RSA for their several use cases. As we do understand, there are new algorithms that have come up because there have been advancements in mathematics, in cryptography. But if you are learning cryptography, it is, I would say, quite important that you get a good understanding of what an RSA algorithm is all about. So I would say in the next video, we will really do a proper deep dive. We'll try to do some mathematical calculations. We'll do it together and see if you are able to understand how the RSA algorithm works behind the scenes. Thanks for watching. So in the previous video, we had a look at what an RSA algorithm is all about. In this video, we will take a look at how an RSA algorithm works under the hood. So now, as I told you, that all we are doing is when we are working on encryption and decryption, we are working with prime numbers. And I always tell you that in the real world, you are actually working on very large prime numbers. But here, the example that we'd be doing, we are just taking simple numbers to understand the whole algorithm. So just to get your understanding on this, I would suggest that please try and keep a pen and paper ready when you are working, and try and work with me. So on your left side, you will actually see the whole process, what RSA algorithm is all about, right? But the first part talks about key generation, because we need to come up with a public key and then we need to come up with a private key. So you come up with a key pair that is public key pair, public private key pair, right? And then at the end of the day, what is our aim? Our aim is to encrypt and our aim is to decrypt. But how does this whole thing takes place? Let's see how it goes under the hood. So first it says we need to select the value of P and Q. As I told you that both the P and Q should be prime numbers. Now, if you may ask that what is a prime number? A prime number is a whole number that can't be divided by any other whole number. So, and we say that the only factors of that number are 1 and the number itself. So here we are choosing very simple prime numbers, like the value is P is equal to 3 and Q is equal to 11, right? What does the second part say? The second says calculate the value of n as P times Q. Very simple. So we are computing the value of n as P times Q. So P times Q, we know P is 3, Q is 11. So 3 times 11 is 33. Up to here, I think it's all good. Then it says you need to calculate the value of phi n is p minus 1 times q minus 1, right? So we look here. So computing the phi n is p minus 1 times q minus 1. P is 3, so 2 minus 1. 3 minus 1, 2, and q minus 1. Q is 11, so 11 minus 1, 10. So 2 times 10 is 20, right? So you get the value of phi n as 20, right? Up to here, again, all good. Then it says you need to select integer e, right? So we need to come up with a value of integer e. Now, how is that integer e? How is that related? What it says, the whole thing can be translated as this, where we are saying choose e such that 1 is less than e is less than phi of n. So I can say that 1 is less than e is less than, what is phi of n? 20. Very good. So we are saying choose a value of e which is between 1 and 20, and it should correspond to this value, which is GCD phi of n, and e is equal to 1, right? And what we are saying is that e and phi n are both co-prime. So let's say we choose or we get the value of e is equal to 7, because if you see 7 is comes in between 1 and 20. So we are saying it is 7 is the number. It is also co-prime, right? What does it say next? Next it says calculate the value of d, right? So how you get the value of d is, it says e to the power of minus 1 modulo phi of n, right? So again, you can translate this into this, where it says d times e percent phi of n equal to 1. So what is d times e, right? So here we are saying the value of d times e, we are now taking the value of d as number 3, right? So we are saying 3 times 7 is 21, 21% 20 is 1. So all you're getting is you're getting the remainder, right? When we say modulo, we are actually talking about the remainder, right? Okay, I think it's pretty good till now. So then it says you need to now compute your public key. So now we have all the values with us, right? We have the value of n, we have the value of e, we have the value of d. So the public key, how the public key is comprised? The public key comprises of e comma n, and the private key comprises of d comma n. So if you see, there are certain similarities, or a part of it is like n is actually being used both ways. So that's why we always say it's a key pair, right? They are kind of intertwined, interlinked to each other. Now, pretty simple. Public key is e comma n. So by now we know that e is the value 7, and 7 we give, and n we give the value as 33, right? So 33 we get from here, and we get 7 comma 33. Again, private key is d comma n. So we know that d we got the figure from here, which is number 3. And the value of n, as we see here, is 33. So we get the public key as 7 comma 33 and private key as 3 comma 33. Pretty simple. You are with me by now. I think if you're still feeling confused, it is pretty simple. Just trust me. Just take a pen and paper. Just try and work through these calculations, and they are all given here, and you can work alongside it. Next, it says, okay, now your input is a plain text, and we need to encrypt it to get a ciphertext. And how do you do that, right? So what it says is that for encryption, what you need to do is, or to get a ciphertext, it should be m to the power of e modulo n, right? So what we are doing is, let's say the value for m is 2, right? So it is saying c is equal to 2 to the power of 7. So now you can think of 2 as your plain text. We are saying 2 to the power of 7 percent 33, right? So what is 2 to the power of 7? So 2 to the power of 7 is 128, right? So we are saying divide 128 by 33. And if we do that, we take 3 times 9, 3 times 3 is 9, 3 times 3, 9. And we get the remainder as 29. And if you see, this 29 corresponds to this value 29, right? So we have encrypted our plain text 2. How did we do that? We said plain text to the power of 7. Now 7 was the value e, right? E, this one, which is 7, right? Percent 33, 29. Now, what is decryption? We all know by now that decryption is nothing but the reverse, wherein your input becomes your ciphertext, right? So here the input is ciphertext, right? Now I need to go back and get my plain text. How do I get my plain text? I start with my ciphertext and I raise it to the power of D, right? What was D? We remember D is 3. So we are saying that's why your input is your ciphertext, this one, which we got here in the previous encrypted output, and we are saying 29 to the power ciphertext to the power of D %33, right? Again, we're getting a modulo. Basically, we're getting a remainder, and that's the good thing, right? So you'll see this was your plain text, right? We encrypted it to a value 29. Then we use the 29 value. We decrypted using our algorithm and we got the value back as 2, right? So all I wanted to show you was how this whole thing of encryption, decryption takes place, how you start with your plain text, you encrypt it and get a ciphertext, how you use the ciphertext, apply the key and you get your original text back. Very important. And another key thing, please remember that since 2015, NIST has recommended that a minimum of 2048 bits keys for RSA should be used, right? It's a clear recommendation from NIST that you shouldn't be using a smaller key length or whatever. Just I showed it was anyways for an example to understand how it works under the hood. So please remember you use larger key sizes. If you use smaller key sizes, as I told you previously, they are always susceptible to brute force attacks, right? So always remember NIST recommends that a minimum of 2048 bit keys should be used, and it's the recommendation. So I believe you would have got good understanding how RSA algorithm works under the hood. Thanks for watching. So after getting a very good understanding of the RSA algorithm, it's time to move on to the next important algorithm, which is the DSA algorithm. Now, what is DSA? So DSA basically stands for a digital signature algorithm, right? So DSA, digital signature algorithm. Now you might ask that, okay, we are studying digital signature algorithm, but what is a digital signature, right? So a digital signature is nothing but a digital code. Now that digital code is generated and authenticated by public key encryption, which is actually attached to the message or to the document to verify the contents of the message and also to verify the sender's identity. That's quite important, right? So digital signature algorithm was actually developed by NIST. So by now we all know what NIST is. NIST is nothing but the National Institute of Standards and Technology. Now again, behind the scenes, it's all advanced mathematics, right? So a digital signature algorithm, and we'll see in the next video like how it works under the hood, but again it's actually based on mathematical concept of modular exponentiation and discrete logarithms. So modular exponentiation is nothing but the exponentiation which is performed over a modulus, right? So again, for the moment I'll say it's just advanced mathematics that it's all based on. Very important point. DSA is a public key algorithm, right? Now by now we know that we are understanding or talking about asymmetric, right? So asymmetric is always multiple keys, right? You have a public private key pair. Now the main thing to understand here is, please don't get confused with digital signature algorithm. It is only used for digital signatures, right? So no encryption or decryption of messages is being done, right? So please remember that. So it's only the digital signatures. Now you might ask, but you have a concept of keys? Yes, we do have a concept of keys, but these keys are used for either signing or verifying the messages, right? So there's a difference we need to understand. In RSA, what we were doing, in RSA, we were actually encrypting original text and generating a ciphertext, transmitting it over the wire, right? But here, what we are saying is we are using the pair of keys, but we are using the pair of keys to just sign the document. And then you're using the other key to verify the messages, right? So quite important. Now, you might remember when we discussed a Joy and Aileen example where Joy had to send a message to Aileen and Joy was signing with his own private key, and then Aileen was decrypting it using Joy's public key because it was available. That's the same concept we are using here. The signing key is actually kept secret, which means we are signing with a private key, and you are on the other side, then you are verifying it with the public key, right? So because it's a public key algorithm, you have a public private key pair, you sign with your private key, and then on the other side, you use the public key for the verification. Now, you might remember when Joy and Aileen example we took, we said that this gives you integrity and authentication. So, which actually shows that Joy is an authentic source. It's basically this message or this document is coming from an authentic source. So you can basically trust on that person, right? So, a very important, DSA generates signatures that are unique to the message, right? Which are being signed and the signing key used. So there is a concept of, in digital signature algorithm, they use a concept of random key. So because of that, you will always see the DSA will generate the signatures that are unique to that. Again, quite related to the first part that we discussed, that signature can be verified by anyone. Why? Because it's through the public key, right? Public key is available to everyone. So Joy's public key, let's say, is available to everyone because it's public, right? But it's signed using a private key. That's why it says the signature can be verified by anyone who has the verification key and the original message. So you need to have the original message and you need to have the right public key available with you to actually verify it. Again, talking about Joy and Aileen's example, again, I keep going back. You might remember when I said if Joy signs using his private key, it means that we are talking about authenticity, integrity, and non-repudiation. So again, I'm just repeating it, but you might remember we said that the message has come from an authentic source and that message hasn't been tampered at all. This is what digital signature algorithm is all about. So again, RSA was used for multiple things, multiple use cases. RSA, you could use RSA algorithm in encrypting, decrypting documents. You can even use for digital signatures as well. But DSA is purely used for digital signatures, and it says DSA has been widely adopted and used in many applications including secure communications, e-commerce, and digital document signing. This is the perfect and the main use case for DSA. Again, DSA is a standardized algorithm, and very important, there are certain parameters you need to give to the DSA algorithm. So when you're working with DSA, there are certain well-defined parameters, and these parameters have been defined by NIST, the National Institute of Standards and Technology. So you need to adhere to those rules. So you can't just simply give any parameters you like. You have to give the parameters that have been specified and given or recommended by NIST. So quite important, guys. So after studying RSA, we have got a very good understanding of what a DSA algorithm is all about. It's a digital signature algorithm. I hope you liked the video. Thank you. Hello. So after having a very good understanding of the RSA algorithm and the DSA algorithm, it's now time to move on to another important algorithm, which is the Diffie-Hellman algorithm. And again, folks, just like what we saw in RSA, the real geniuses, they are actually in front of you now. So these are the guys who actually invented the Diffie-Hellman algorithm, which is actually named after their names itself. So let's try and understand what is a Diffie-Hellman algorithm, right? So the very first thing is it's a public key exchange algorithm used for secure communication over an insecure network. That is the key here. So by now, I think everybody who's taken my course now would understand when we are saying public key exchange, you can easily make out, yes, we are talking about multiple keys So it's different from a symmetric algorithm or a symmetric key. Definitely it's asymmetric key where there would be some kind of key pairs, right? So it is a public key exchange algorithm. Now that is another thing that we need to understand here, the usage of Diffie-Hellman algorithm. Now with RSA, we figured out that RSA can be used for encrypting the messages, and it can also be used for digital signatures. With a DSA, we figured out that it is an algorithm which is actually used mainly for digital signatures. But now, what is the usage of Diffie-Hellman? So Diffie-Hellman helps you to have a public key exchange. So it allows a mechanism in which you can exchange, or both the parties can have the same keys, right? But the magic here is that you have to use secure communication over an insecure network like internet, right? And we will see how this whole magic happens, and we will take an example of coloring scheme. I'll show you where two people, Alice and Bob, will be talking to each other, and eventually they start with same colors and end up encrypting each other's messages, and then they come up with the shared secret, right? So as we now understand, it was invented by Whitfield Diffie and Martin Hellman in 1976. So just think about it, that back in 1976 they invented it, and till date it is being utilized. So please have a good understanding of how a Diffie-Hellman algorithm works. So Diffie-Hellman allows two parties to establish a shared secret key, and that is the aim, right? Both the parties will have a shared secret key. Now, just think about what we learned in symmetric encryption, and that was the benefit of symmetric encryption. Once both the parties have the same key, it uses less computational power, and it is far quicker as well, right? And it gives the speed to the algorithm as well. So that is what is the main aim. So first you need to establish a shared secret key so that the sender and receiver know that, okay, if I have to encrypt, I need to use this key, and I need to decrypt, I need to use this key, right? Without having to exchange the key directly. That is the magic, right? So you're not sending your key over the wire, but you will be sending the encrypted key, and then based on the decryption and based on the algorithm you use, eventually you'll end up having same key on the sender and receiver. If it is becoming confusing, don't worry, we will take up in the very next video, we will discuss how this works using a color mechanism, right? So Diffie-Hellman is based on the difficulty of the discrete logarithmic problems in a finite field. Now, again, it's all talking about advanced mathematics. So discrete algorithms or discrete logarithms are the logarithms which are defined with regards to the multiplicative cyclic groups, right? So, and now you might ask, okay, but what is a multiplicative cyclic group or a group? So in mathematics, so I would say in advanced mathematics, multiplicative group refers to one of the following concepts. So it's a group under multiplication of invertible elements of a field or a ring. And again, remember here in Diffie-Hellman algorithm, we are always talking about large prime numbers, right? So there is a usage of large prime numbers, and there is a generator of the prime numbers multiplicative group, and a random shared secret numbers are chosen by each party. Now you can try and imagine about the Joy and Aileen example we studied, where we actually did the hybrid encryption. So I'm writing it down, hybrid encryption. Probably you can visit that lecture one more time. In that is what the main aim was. You are using asymmetric encryption to eventually use the symmetric encryption, right? That is what Diffie-Hellman does. So it is helping you to come up with a shared secret. But how do you get it? You use large prime numbers, you use prime numbers multiplicative group, and you use some random secret numbers on both parties, right? Yes, the parties use their secret numbers to compute a shared secret value that can be used for symmetric encryption key. Exactly. That is what I was trying to explain you, that the aim is to reach to a shared secret key. So once you have the shared secret key, it means if I am encrypting using that shared secret key, the other party can easily decrypt using that secret key, and we don't have to even exchange this information or send the key over the wire. So it is quite important that the aim is, again, that the parties use their secret numbers, but they compute a shared secret key. Again, don't worry, we will take a look at a very simple example from which you will come to know. Okay, so Diffie-Hellman provides perfect forward secrecy, right? So which says that if a private key is compromised, the past communication cannot be decrypted, right? It's always based on that. So what is a perfect forward secrecy? Now, a perfect forward secrecy is a style of encryption that enables short-term private key exchange between a client and a server. And it accomplishes this by utilizing unique session keys that are generated automatically. That is the key here. The session keys are generated automatically each time a session is made, right? So always remember, Diffie-Hellman gives you forward secrecy or perfect forward secrecy. Now you may ask, okay, in which applications, what are the different use cases where Diffie-Hellman is being used? Yes, they are the most important ones. SSL, secure socket layer, TLS, transport layer security, SSH. And so let's say if you are actually doing an SSH to a Linux terminal, right, you would be using the SSH protocol, and we'll be studying all these protocols as well. And VPNs, virtual private networks. So all these are the wide applications where you would be using Diffie-Hellman. Again, we are learning standard algorithms, standard algorithms which are recommended by NIST. And we already said that these are all the ones that are standard, say, algorithms. So Diffie-Hellman has been standardized by various organizations, not only NIST, but also IETF, which is the Internet Engineering Task Force. So that way you can say that you can very well rely on the Diffie-Hellman algorithm in your applications. Now, the biggest challenge with Diffie-Hellman is, as I said, that you are not really sharing, you're not sending the key itself, but you are sending the key in some form of encrypted manner, right? So that is where the Diffie-Hellman is vulnerable to the man-in-the-middle attacks. And by now you, I guess, are already aware of what a man-in-the-middle attack is. Basically, you're a hacker, right? Who's trying to get the encrypted message and trying to decipher out of it that what that shared secret key is. So right, so it's vulnerable to man-in-the-middle attack, where the attacker intercepts the communication and alters the shared secret, right? So just imagine if the hacker is changing your secret key, then the hacker can start talking to the receiving party, and the receiving party would feel, oh, that's good, right? Okay, I'm talking to this guy, and this is an authentic source. Now comes a very interesting thing that we already learned, but how can you prevent this? Yes, you can prevent it using additional cryptographic mechanisms such as digital signatures. Now I can ask you, and if you close your eyes and give me the answer, why would you use digital signatures to prevent man-in-the-middle attacks? Okay, so let me try and explain you. So the thing is that what we learned from a digital signature was, because you were signing using your own private key, which means that it gives you that the message or the source is an authentic source, right? So that's where we said that you are getting integrity and you are getting authenticity, right? So this is where we are combining both the things. So with Diffie-Hellman, what we are saying, if it is prone to man-in-the-middle attack, why don't we have additional cryptography mechanism on top of it using digital signature? Because that would give you the integrity. That is all we want to make sure, that the source that we are talking to is the authentic source. So guys, thank you for watching. In the next video, we will take a look how the Diffie-Hellman algorithm works under the hood. So we'll do it using a color coding scheme. Thanks for watching. Okay, so welcome to another interesting video, and in this video we will learn how the Diffie-Hellman algorithm works under the hood. right? So I told you in the previous video, the main aim of a Diffie-Hellman algorithm is to have a shared secret. Basically, once you have the shared secret, then eventually you can actually utilize your symmetric key, because if the sender and the receiver have got the shared secret, then they can easily encrypt the message and decrypt it using the shared secret. And that is what the aim of Diffie-Hellman algorithm is. Now, let's take a look how this actually works behind the scenes. So here we are taking an example and we'll go very slow. So Alice needs to talk to Bob, right? Alice and Bob, we are taking it as two parties. You can say they are the sender and receiver, and they need to talk to each other and in an insecure environment, right? So you could say they are talking to each other on an internet, right? So what happens is we will try and understand using color coding, or you can say color mixing as such. So you can take yourself back to the days when we used to study in primary school and we used to mix colors, right? That is what we'll be doing now. So what it says is, first of all, Alice and Bob decide to have a common paint, right? First of all, you decide, Alice tells Bob and Bob tells Alice, hey Bob, let's try and work on a common color, right? Alice says, okay, yellow, and Bob says yellow, right? So by this time, both the parties know that yes, yellow is the common color. We need to start with yellow. Okay, you start with yellow. Now comes the part where you need to use your own secret color, right? This is secret to Alice and secret to Bob. So let's say Alice says, okay, I'll pick red color, but you don't have to tell anybody, right? Alice is not telling that secret color to anybody. Same way, Bob is coming up with another secret color, and Bob is not telling that secret color to anybody, right? Good till this point, right? Now, if you may ask, what are these secret colors? Just imagine in computers or in mathematics, it would be large prime numbers. Again, we are always talking about large prime numbers. We're not talking about small numbers, but large prime numbers you are talking about, right? So now comes the concept of mixing, right? So we are mixing the colors. So, okay. So what we are doing is we are taking this common paint that we took plus the secret key that we took, or the secret color, and we are coming up with something like an orange color here. So Alice is coming up with an orange color, and Bob does the same thing. So Bob uses the common paint, his secret color, and gets something like a blue, right? So Alice has come up with an orange, Bob has come up with the blue. And this is the thing that happens here, right? Now, Alice says, okay, let me send this over to Bob, and then Bob sends this to Alice. So an exchange of information is taking place, right? But the key here is, if you read this, this is a public transport happening, and very important, assume that the mixture separation is expensive, right? What does that mean? So what it means is, let's say if a hacker or a man in the middle comes and tries to read this, they won't be able to separate it out, right? It is at that level. Let's say a hacker gets this orange color or a hacker gets this blue color. They shouldn't be able to separate the colors to get that, oh, this blue has been formed with a combination of a yellow and a secret which is orange, right? So that is where the strength or the robustness of the algorithm comes. It should be really strong algorithm and really big prime numbers that you should be using, that even if a hacker comes, they can't separate this mixture out. Very important. Okay, so going back. So let's say now Alice has got the color that was sent by Bob, and Bob has sent got the color that was exchanged by Alice, right? So now both the parties have got the mixed colors, I would say. Okay, now comes the magic, right? The magic is, now Alice will apply its own secret color here, right? So it's the same secret color that Alice had chosen in the beginning. Now Alice will mix the blue with her own secret color to get a new color, which is brown. And Bob will do the same thing. The exchange information that Bob got, Bob will be mixing the same secret key and applying that to get the color. And if you see, happy days, because you have got the same secret key, right? So now both the parties, Alice, Bob, have got their common secret, right? Nobody knows that apart from Alice and Bob, and they have made it possible over a public internet. Even if a hacker tried to get that, they won't be able to understand. That is the beauty of this algorithm, that even on a non-secure, insecure network, you are able to perform a secure communication, because once you come up with your common secret, then I can encrypt, I can decrypt using the same secret, which gives me hybrid encryption, or you can say which would allow me the symmetric key encryption, which is much faster, which uses less computational power. So I guess by now you would have got a good understanding of how a Diffie-Hellman algorithm works under the hood. Now in the next video, we will actually try and start working on some numbers. We'll do some mathematics and see how this color mixing or the paint mixing that we learned can be applied to the actual Diffie-Hellman algorithm. Thanks for watching. Hello and welcome to a very interesting video on Diffie-Hellman under the hood using mathematical calculations. So in the previous video, we understood how the Diffie-Hellman algorithm works. We took the example of paint mixing, where Alice and Bob came up with a common paint. They selected their own secret colors, came up with a new paint. As you can see here, Alice comes up with orange and Bob comes with specific color. Then they exchange these paints and then add on the secret color for each of those. And then they eventually get back the common secret, which nobody knows of it, and only Alice and Bob knows it. But let's say how mathematically it works. So mathematically, how it says is that where we said that both Alice and Bob come up with a common paint, which is yellow. In terms of mathematics, it says, so Alice and Bob begin by deciding mutually two numbers. So the important thing is both Alice and Bob are aware of these numbers. And in mathematics, we call these numbers as modulus of P and base G, right? So you can think of it that both Alice and Bob are aware of these two numbers, and you can map these to your yellow color, right? So you can think of it as your yellow color, what we just learned in the example, right? So, and it says in practical use, modulus P is a very large prime number. As we've always said, when you're doing encryption, you always choose very large prime numbers, and base G is normally a small number for calculations, right? So, and we say that, okay, we choose the value of P, modulus P is 17 and base G is 4, right? Now, what we say is once they have mutually decided on these numbers, Alice settles on a secret number and Bob settles on a secret number, right? So here we are talking about this. So let's say Alice chooses a secret number as A equals 3 and Bob chooses B equal to 6, right? So we said this yellow color corresponds to modulus P and base G. The value for modulus P is 17, base G is 4. Now Alice chooses a secret color orange, and that is value is A equal to 3, and Bob chooses his own number, the value is B equal to 6. These are kind of, you can say, secret or private to Alice and Bob, right? Now we are doing a mixing, right? The mixing is happening. How this mixing is happening? So this mixing happens using a mathematical calculation, which is A equal to G to the power of A modulus P. So now what is A? We know G is, our base G is 4. So 4 to the power of 3 modulus of 17, which means 4 times 4, 16 times 4, 64, modulus 17. So it is basically you are dividing and you're getting the remainder. So you get the value as A is 13. So just remember, this is A equal to 13. So this is capital A, and in first instance it was small a. So now we got the color, the mixed color, which is for Alice, which is A equal to 13. Same way Bob will be doing some calculations and getting his own color. So how Bob does it as 4 to the power of 6 modulus 17, right? So same way you see that the value for B equal to 16, right? So it's 4 to the power 6 modulus 17. It's clearly stated here. You can multiply on calculator as well. So 4096 modulus 17, right? You get it as the value of B, right? So we get the value of B is 16, right? So in the next stage, we said this gets transferred and this gets transferred. And we clearly stated that so mixed color is getting transferred. So even if a hacker comes in, the algorithm should be so complex that the hacker shouldn't be able to separate them out, right? So now we say, okay, B equal to 16 comes here, right? And A equal to 13 goes here. Perfect. Now what happens? Now the next stage is we are saying Alice needs to apply her secret key and Bob needs to apply his own secret key. Let's see how mathematically it works. So when you're doing it mathematically, we call it the S as B to the power of A modulus P. Now B we know by now is 16. So 16 to the power of 3 modulus 17, because P we said is 17, right? So we get 16 to the power of 3 modulus 17, we get a figure as 16. So this is my now secret key as 16. So if you see this color is my secret key as 16, right? But the magic should be that we should eventually end up with S equal to 16 here as well. So let's take a look. Yes. So now the secret key is A to the power of B modulus P, because here it was B to the power of A modulus P. Here it is A to the power of B modulus B. Now A we know it's 13. 13 to the power of B. B is 6. Modulus 17 is this big number, modulus 17. So you're left with the remainder as 16. So perfect. So now we have got S is equal to 16, right? So we have eventually reached to the common secret. Now, as I told you in the previous video, once you have got your common secret, you can achieve symmetric encryption, right? You can encrypt using this secret key and decrypt using this secret key in a very, very secure manner. So I believe this video was quite interesting for you. If you are getting confused, I would certainly request you to watch this video a couple of more times. You can go slow, you can take pen and paper and work on it. These are simple calculations. You just take the example of the color coding on your right side and look at the mathematical calculations on your left side. Thanks for watching. Hello and welcome. So it's time to take a look at another interesting algorithm. We call it the ECDSA algorithm. Now, what does ECDSA stand for? So ECDSA stand for Elliptical Curve Digital Signature Algorithm, right? So as the name suggests, it is an algorithm which would be used for digital signatures. And the EC stands for elliptical curve. So let's take a look. So ECDSA is a digital signature algorithm that is based on elliptic curves. Now you may ask, what are elliptic curves? So an elliptic curve is a plane curve over a finite field, which is made up of points that satisfy the equation y equals x cubed plus ax plus b, something like this, right? This is actually an elliptical curve. And this is how the entire elliptical curve algorithm is based on. And what it says is that any point on the curve that can be mirrored over the x-axis, the curve will still stay the same, right? So quite important. It is part of the advanced mathematics, I'd say, the elliptical curve, and you can always read about it, what are elliptical curves, but this is how it actually goes about, and this is the kind of formula it uses. Okay, let's take a look further. So it was developed as an alternative to the traditional DSA and RSA, right? Quite important. So the RSA algorithms, the DSA algorithms, they were already there in the market, right? But the scientists or the cryptographers, they wanted to work further on it or wanted to improve upon those algorithms. That's why these the elliptical curve algorithm came as a alternative to those. Okay, so ECDS is a public key algorithm. I think by now I have already repeated myself so many number of times that what is a public key algorithm. So from here you can easily make out that it is made up of pair of keys, right? So there would be a public private key pair, and it's not like a single key is being used for encrypting and decrypting, right? So it is more of related to the asymmetric keys, where you will have a public private key pairs. And as the name suggests, digital signature algorithm, it means these keys are used for signing and verifying messages. Now, it says the signing key is kept secret by the signer, right? While the verification key is made public. So as we know, there's a public private key pair. So the sender is actually signing with his or her own private key, right? And then you are sending it over the network. And who can say decrypt it? Only the signer's public key, which would anyways be available to anybody. So anybody can open that, but all it says is that the message can't be tampered. Or if it is tampered, you can easily come to know, right? So this is where the digital signatures come into picture, that you need to ensure that you are the guy who's actually sending that information across, right? So it's very important. The signing key is kept secret and the verification key is public. Oh, and another key point, guys. So you might remember that with RSA keys, we kept on increasing the length of the keys that have to be used. So there was always a recommendation from NIST that with RSA, you need to have bigger key lengths. The beauty about ECDSA is it says that even a 224-bit elliptical curve can provide the same level of security like a 2048-bit RSA key. So just think about it, that it's so powerful that even a smaller key can actually achieve the similar kind of benefits, right? Good. So the signature can be verified by anyone who has the verification key and the original message. So as I said, all we are trying to ensure is that you are the right person, or we are authenticating in a way that it's actually sent by the right person and it's not being tampered, or it's not a hacker is sending us the message. So you just need to ensure that the signature can be verified by anyone who has the verification key, which is a public key. And now we have already learned about it. I won't go into the details of it. As you might remember, when we did the Alex example, and also the Joy and Aileen example, we clearly said that if you're signing with your private key and you're using a public key to decrypt it, it means that it gives you three things, which is message authenticity, integrity, that nobody has tampered with your messages, and non-repudiation, right? We've learned about it in previous lectures. So, and yes, it says elliptical curve digital signature algorithm is considered to be more secure than DSA and RSA. Why? Because it's, as I said, it's based on advanced mathematics and the advanced mathematical properties of elliptical curves. It's quite complex algorithm. So it's considered to be definitely more secure than RSA and DSA. And just to talk about some use cases. ECDSA is normally used in applications including secure communication, where you need to ensure secure communication, e-commerce, like you're doing some transactions online, and digital document signing. Let's say you are purchasing a property, right? You are asked to digitally sign a document, or say the lender would send you a document and say, please, can you digitally sign it? So all we are ensuring is you're the right person who's doing it, right? And it is a standardized algorithm. So very important that the parameters that you specify for ECDSA, you have to go with what NIST or ISO has given us. It's not that you can just specify any parameters in ECDSA algorithm. So you have to be careful that you only specify the parameters that have been specified by NIST or ISO. With this, we come to the end of the video for ECDSA. So just another interesting algorithm that we learned. Thanks for watching. Okay, so it's a blank screen in front of us. Yeah. So the thing is that a lot of times I'm actually asked by a lot of folks that, okay, now we have got an understanding of what an RSA algorithm is, what a DSA is, what an ECDSA is, and what a Diffie-Hellman is. You've actually taught us so many different algorithms, but we are really kind of confused where to use what and what's the difference between each algorithm. It's getting so kind of confusing in the mind, right? So I thought, why not come up with a slide which actually shows you each algorithm and shows and talks about the pros and cons of each algorithm. So let's take a look. So the very first algorithm that we learned was the RSA algorithm, right? So with RSA, what we said was it's the main pros of RSA are it's widely used and supported by many systems and software. So I think you might remember I told you that RSA is the oldest and the most widely used algorithm in cryptography, right? And it offers excellent security and has stood the test of time. Very important thing, right? It has stood the test of time means that it is so old, right? It came somewhere back in 1977, even before I was born probably. And still it has stood the test of time, which means that over the period of time, it's still being utilized, right? Even today, it is being utilized. If it was, not that strong, I'm sure it wouldn't have stood for that long, right? It offers good key sizes. So the good thing about RSA is that you can have humongous key sizes, a big, massive key sizes. Like NIST started recommending that you should have at least 2048 key size. But what it says is that that is also a pro of this algorithm, that it offers key sizes of 2048, 3072, 4096 bits. And very, very important point, guys, it is good for encryption and digital signatures. So that's the beauty of RSA. Normally, when we studied other algorithms like DSA or ECDSA, you might have noticed that they were the algorithms which were there for digital signatures. But RSA algorithm is actually there for encryption as well as digital signatures, both. Now, yes, there are certain cons, and they are that this is actually slower than some other algorithms. Now, in a way, you can say because ECDSA and DSA were fairly new algorithms, so definitely they would have looked at the existing RSA algorithm, and definitely if it was slower, they wouldn't have brought those things over in the new algorithms, right? It is vulnerable to attacks, but only if you are using a small key size. That's why, as I told you, that 1024-bit RSA keys are no longer considered secure. NIST says that you should be at least at 2048 bits. So quite important, if you are using RSA, please go with large key sizes. And it also says that sometimes the key generation can be slow for large key sizes. Obviously, right? If you are talking about a 4096 bits key, such a big key if you're creating, then obviously the key generation can be slow for large key sizes. Then we looked at the DSA algorithm, right? So what are the pros with DSA? So it says it's faster than RSA, but remember, it is actually used for signing and verifying digital signatures, unlike RSA, which is actually used for encryption and digital signatures. The good thing about DSA is it requires smaller key sizes. So you can actually just use smaller key sizes compared to the equivalent security with RSA, right? And it says that it gives strong security when implemented correctly, which means that you are using the right key size, you are using the right parameters, then you can achieve good amount of security if it is implemented correctly. But yeah, few cons. Now, as compared to RSA, it is less widely used, right? Because as I told you that RSA is more widely used, very popular. So it is less widely used than and supported than the RSA and ECDSA. Again, quite a comparison with RSA, it is only suitable for digital signatures, right? It is not suitable for encryption because with encryption, you can use RSA, right? It's vulnerable to certain type of attacks such as collision attacks if used incorrectly. So very important, as I said, you are having the right key size and you're having the right parameters so that you are not vulnerable to any attacks. Then we learned the much newer algorithm, which was the ECDSA, which is elliptical curve digital signature algorithm. So the biggest pro is that it is faster and more efficient. Why? Because as I said, that it is based on elliptical curves, which is an advanced mathematic techniques, and it is fairly new. So definitely they would have thought about how they can make an algorithm which is better than RSA, which is quite old. It offers strong security with smaller key sizes. So as we said that if you're using a 224 key size or if you're using a 2048 key size for RSA, it's kind of equivalent, right? So with ECDSA, if you are on 224 bit key size, that is equivalent to 2048 bit key size, which makes this as a biggest pro for ECDSA, that you can get the same amount of security with smaller key sizes. And it's widely used in mobile and IoT applications. So IoT applications are Internet of Things, we call it. So it's actually being used for that. There are certain cons. It is less widely used and supported than RSA. Again, we are comparing with RSA. Everything goes back to RSA, right? The Revis-Sherman algorithm, Shamir algorithm. So it is less widely used and supported than RSA. The key generation can be slower than RSA for large key sizes. Again, the problem with ECDSA is because it's based on the mathematical or elliptical curves. If you're going for very high or big size keys, then the key generation can be slower, right? It requires careful selection of elliptical curves. The elliptical curve itself is quite an advanced and complex mathematical technique. So you need to be very careful. You need to be really good at mathematics to get the required selection of elliptical curves to avoid any security vulnerabilities, right? Then we also learned the Diffie-Hellman algorithm, very important one, right? So the Diffie-Hellman actually allows for secure key exchange. So you might remember the video where we did the colors, right? You were sending the colors to each other, right? So then the main criteria was that you need to send across the key, but the hacker shouldn't be able to know that which key you are sending. So we always used to encrypt the key and then send it across. So it allows for the secure key exchange without the need for pre-shared keys. So you're not using any pre-shared keys, but you have your own keys. Then you come up with your own secret keys. You apply those and then you do that, right? Okay, good. So it's actually widely used in VPNs. Now, what is a VPN? VPN is a virtual private network, and we will look about VPN in upcoming videos. So it's widely used in VPNs and other applications that require secure communication. And it is resistant to eavesdroppers and passive attackers. The biggest con with Diffie-Hellman is it's vulnerable to man-in-the-middle attack if not authenticated. If you don't use it properly, then Diffie-Hellman algorithm can be vulnerable or susceptible to the man-in-the-middle attack, right? And it requires careful management of shared secrets to prevent unauthorized access. So when you are actually sharing the secret, you have to be really careful that you use the right keys, the right key lengths. Only then you would achieve the right results. So guys, I think this should really give you a good understanding of all these approved algorithms and how we can compare them with each other. Thanks for watching. Hi folks, welcome back. In this video, we will take a look at what is PKI, or the public key infrastructure. Let me tell you guys, this is the most important thing after encryption. PKI, public key infrastructure. What I want to tell you is, if PKI was not there, then today you and me would have never done digital banking. So what I want to say is, then the kind of the peace of mind that you have when you go to hsbc.co.uk, icicibank.com, or even let's say facebook.com, where you are posting your pictures, right? You have that peace of mind that you are actually interacting with Facebook, or you are actually interacting with HSBC. You are putting your, say, credit card details when you are shopping at Next, right? Or you are shopping at MX, whatever e-shopping we are doing, or Myntra.com, right? So because we have that peace of mind that the server with which we are talking is the right server. It's actually not a hacker, right? So this is what a PKI gives us. So the PKI, it's a set of technologies and protocols. Very important. Protocol is nothing but a set of rules which is used to secure the online communication. So you can say it is a form of internet encryption. And it is how a web browser communicates to the web servers. So as I said, if PKI was not there, maybe today we wouldn't be doing online shopping, or maybe today we wouldn't be doing transactions online, right? So PKI is based on asymmetric cryptography. Now you can imagine why we studied asymmetric cryptography, right? Because if we hadn't studied asymmetric cryptography, we wouldn't have understood the importance of PKI or how PKI works. And by now, I think everybody who's watching this video can raise their hand and say, I know asymmetric cryptography. Asymmetric cryptography means that you are using, yes, you are using a public and a private key pair. It could be used either for encrypting or for decrypting. I always tell, you can either encrypt using a public key and decrypt via private key, or you could encrypt via private key and decrypt via public key. So it's always these kind of use cases which are there. Very important things, and we'll learn about these as we go forward. The main components of a PKI, and these are the new terminologies that you'd be learning, are CAs. We call them certificate authorities, a CA, right? And the other thing is we learn about digital certificates. Now, we talked a lot about digital signatures, how these digital signatures were happening. You were signing with your private key, you were sending it across, and then you were using the public key to get the message back, right? So that is the digital signature. But here we will learn digital certificates, and always remember these digital certificates are issued for the servers. So as a client, you won't go and get digital certificates. It's always the servers. So what it wants to say is, yes, I am Facebook.com or I am ICICIbank.com. So it is the responsibility of the server to have the right certificates, or digitally signed certificates, we can call it. Right, then we have something called CRLs. This is certificate revocation lists. And we have the registration authorities, the RAs. Let's take a look. So a CA. CA is responsible for issuing the digital certificate, right? So CA stands for a certificate authority, right? So what I'm saying is that a CA is responsible for issuing digital certificates. So think about it as an organization which is issuing digital certificates, right? So there's a concept called digital certificate, but there's a body. It's an organization or a body which is actually issuing these digital certificates. So one of the biggest CAs is DigiCert. You will learn about it, and you'll see, we will see in another video. We'll go through their website to see what kind of services they're offering. Then there is another big CA called Comodo, right? These are like big names from where the servers get their digital certificates. So a CA is responsible for issuing the digital certificate, which are used to verify the identity of the entity in the online transaction. Now, a very important point, the digital certificate contains the identity of the entity, right? When I say entity, this is, let's say, your Facebook, right? Or your ICICI or your HSBC, right? That's what we are saying. So digital certificate will contain the identity of the entity being verified, as well as its public key. So HSBC will be putting their own public key inside that digital certificate, or that certificate which is then signed by the private key of the CA. Very important. See how closely knit this thing is, that the digital certificate contains identity. So because how would you then identify, or how would make sure that you are actually Facebook.com? You're not a hacker.com, right? You're not a hacker sitting somewhere and imitating as Facebook. So digital certificate contains the identity of the entity. I'm also putting my public key, and we will see in an example how this whole thing works. And the certificate is signed by the CA to ensure its authenticity. So we learned about CRL, but what is a CRL? So CRLs are nothing but the list of digital certificates that have been revoked. So you just put in your digital, certificate, you put all the list of all the digital certificates that have been revoked so that they can't be used. Oh, very important point is RA. Now, to understand RA, just think about it that CA is the big organization which is actually issuing certificates to people. But what it has done is that it has delegated the checking to the RA. So RA is responsible for verifying the identity. So let's say if today I'm cloudalchemy.com, I go to a CA, I can't just simply go to the CA and ask them for the certificate. What they'll say is, first the request goes to the RA. RA will verify me. RA will verify, okay, I am cloudalchemy.com, this is my website, or this is my web address, and this is where I'm hosted. All these details will be there, right? My entire information will be there. My digital, my checks will be done, right? It would be checked that I'm the right person. It's not somebody is coming and saying that I'm cloudalchemy or I'm facebook.com, right? So RA is responsible for verifying the identity. Very important. Identity is the key word here, right? You are identifying yourself. It's like showing my driving license or showing my passport. Yes, I'm the same person, right? And of entities requesting digital certificate and forwarding the certificate request to the appropriate CA. So once the RA sees that yes, it's all good, it sends the request back to the CA or the certificate authority saying that yes, you can now go ahead and issue the certificate to this person. Okay, so PKI infrastructure, as I said, can help to provide secure communication by ensuring authenticity and integrity of data. So it's a combination, it's a culmination of encryption as well as the digital signatures that we learned. So it says, and I said, it's a backbone. It's the backbone of how secure communication takes place over the internet, right? So you are getting authentication, you are getting integrity, and it helps you to provide confidentiality through encryption, right? Okay, so that's pretty much, I'd say, with PKI. And very important concept, guys. Keep in mind, whatever we learned with encryption, we are going to apply the same knowledge, and these are more advanced topics we'll be learning. A lot of things will be repeated, but it is important to get good understanding of your PKI or the public key infrastructure. Thanks for watching. Okay, so another very important concept that we should learn with PKI is hashing. So you might have seen in one of the previous videos, we talked about hashing when we were describing encryption as well. But what exactly is hashing? So let's take a look at good details. So let's get our pen out and let's take a look. What is hashing? Right. So hashing is a cryptographic technique which is used to transform the data of any size into a fixed length output, which we call the hash, right? So it is fixed length output. So if you see here, if your input is fox, if your input is the red fox jumps over the blue dog, if your input is the red fox jumps something they have changed from over to OUVR and the blue dog, you'll see that you will get always, first of all, you get always the fixed length output. It is always the fixed length output, right? If you see, even if it is just 3 characters or there are 10 characters or 20 characters, it's the output is always fixed length. Another key important thing you need to notice here is that the value that you are getting. So here the red fox jumps over the blue dog, and here the red fox jumps, just small modification. If you see, this V has been changed to a U, and you will see that you get altogether a different output. That is what is the beauty of hashing, right? So cryptographic technique which is used to transform the data of any size into a fixed length output. Now, the hash function takes the input data and produces the hash that is unique to the specific input. So very important. So here you have the plain text, right? you take that plain text through an algorithm, right? And this algorithm we call the hashing function, right? So this hashing function then generates a hash or a hash text, and this is called a digest, and we will see further. So a hash function is, as you see here, this is my hash function. It is taking the input, right? It is taking the input data and producing a hash that is unique to the specific input. The most commonly used cryptographic hash functions are SHA-256, SHA-384, SHA-512. Very popular algorithm. You'll see the hash function, which is SHA-256. Hashing is commonly used in digital signatures. So now you might remember when we did videos on digital signatures, we talked about hashing, but here we are doing a more deep dive on hashing. What exactly is hashing, right? So hashing is commonly used in digital signatures, password storages, and data integrity checks, right? You just need to ensure that your data is not tampered. As you can see, if I just simply change V to a U and rest of the text is same, still I get a different digest, right? The output of a hash function is referred to the message digest. So this output that we are getting is called a message digest, right? So we say it is a message digest. And the process of producing a hash from the input data is called hashing. As you see, I'm taking input data, I'm passing it through a hash function, I'm getting an output, and that output is called a digest. And that function that we are using and this whole process is known as hashing. So easy. Okay, very, very, very important point. Always remember, guys, hash functions are one-way functions. It is a one-way street. You can always go from here to here, but you can't go from here back to here. So basically, you can't take a message digest, pass it through the hash function to get the actual plain text. It doesn't work. So hash functions are one-way functions, meaning that it is virtually impossible to reverse engineer the original input data. So as I said, you can't take this hash digest or hash text or message digest, pass it back through the hashing function to get your plain text. That doesn't work at all. It won't work. The size of the output hash is fixed and is usually much smaller than the input data, making it easy to store and transfer. Because the biggest challenge in internet is sending the message or the data packets, right? So that is where they came up with an idea that instead of using this whole encryption on the message itself, why don't we do it on the digest, which is much smaller. And as I said, it is a fixed size. The size of the output is fixed. So even if here I'm having Fox or here I'm having a big text, the digest size is still the same. Because small change in the input data can result in drastically different hash output, hashes are often used for detecting tampering or changes to the data. Perfect example we have got here, right? Here some hacker came and he or she changed the V to a U, thinking that the other side won't come to know, right? Because if you just read quickly, you might say, oh, it looks quite similar. No, because if you see, the digest has changed. So this digest is different from this digest. And that is the whole base of hashing, that even if you make a small change somewhere, even if you put a space bar somewhere or a space or some character somewhere, your digest will simply change, which will tell the end user that yes, this message has been tampered. So very important, guys, we learned about hashing. Thanks for watching. Okay, so after learning what is hashing, it's time to take a look into a demo for hashing. It's a very, very simple demo. In this, what we will do is, first of all, we'll create a file which is called hello.txt. In that hello.txt, we'll just enter some words. We'll say hello world. We'll use a hashing function and get the digest of that. So the command for that is OpenSSL digest minus SHA-256. So SHA-256, as we know by now, is the algorithm we are using, and we are passing the message or the file as hello.txt. So all we are asking the hash function is, hey, hash function, I'm giving you this message. Can you please create a digest for me? So as you know, it would actually create a long alpha, kind of a hexadecimal digest for you. And then what we will do is we will try to replicate if, let's say, a hacker tries to change the digest, or if the hacker tries to change the actual message, right? So in this case, what we'll do is we'll modify the contents of the file and we'll just simply give one space after hello world, and we'll see that the hash function will automatically generate a new digest. So if you are getting a new digest, automatically you will come to know that, hey, somebody has tempered my original message, because you have the original digest with you, and ideally you would have compared that digest with the new digest. But if the new digest is changed, it means somebody has tempered your message. So that's the beauty of hashing. So let's take a look. So first we need to create a file called hello.txt. So I just do a vi hello.txt, and in that I'll just simply say hello world, right? I save it, and then I will use the command, and you guys can actually work with me on this simple command we are giving. We are just saying OpenSSL digest dgst minus SHA-256 hello.txt, right? Perfect. So what it has done, it has actually given us a digest, right? This alphanumeric output is there, which we call the digest or the message digest, right? Now what I'll do is I'll temper this a bit, and I'll change hello.txt to just enter additional character in this, right? So I've added a character here, and if I say save it, and let's try and create a digest back on that. Perfect. So just have a look. So it's automatically generated a new digest. So as I told you, that even if you put a space, you put a dot, so if your original message is tempered, then automatically the hashing algorithm will give you a new digest. So from here, you can easily compare that my original message digest was this, but now this is this. So it means that when the message came to me, somebody or a man in the middle has tampered with it, and that's why I'm getting a new digest. So guys, this shows the importance of hashing algorithm. Thanks for watching. Hello and welcome. So after having a look at the hashing, or what a hashing algorithm is, or what is a hash function, it's time to take a look at message digest. So we did actually talk about in the message digest in the previous video as well, but this is a more detailed one and a deep dive, I'd say. So I won't repeat myself, otherwise the students would say he's really repeating the stuff, but yeah, we'll just see how it goes. So yes, what is a message digest? So as you can see, this is a message of any arbitrary length. As you can see, you have Fox, you have all these messages. And when you pass it through a hash function like SHA-256 or SHA-512, you get an output, which is a message digest. And this is like something like in this form, right? So all it says is it's a fixed length output produced by a cryptographic hash function when given an input message. The message digest is also sometimes known as, is referred to as a hash value or checksum. So what you are getting in some terminologies, we also call it the checksum. That what is your checksum, right? So it's the same thing. We call it hash value or checksum. Message digests are commonly used in cryptography to provide data integrity and authentication. So how you are getting this data integrity and authentication? If you can see, there's a small change here. A V is being changed or tampered to a U, and you will see that right away you will have a different value of your digest. So this is how you come to know whether somebody has tampered your message, right? A message digest is a unique representation of the input message. Right? Again, it's repeating ourselves. We are saying that it is a unique representation, and any small change, right? Any small change in the message will result in a different message digest, as we saw here, right? The size of the message digest is typically much smaller. So if you see, if I keep on adding text here, if I have, let's say, a big document, even then my message digest size would be the same. So the size of the message digest is typically much smaller than the original message. I think we already learned that this is a one-way street. You can go from here to here, but you can't go from here to here, right? from a message digest, you can't derive your original message. So it's a cryptographic hash functions used to generate the message digest are designed to be one-way functions, meaning it is infeasible to recover the original message. So you can't get your original message back. The signer generates a message digest of the document they want to sign and then signs the digest rather than the entire document. Very, very, very important point. I would say please bookmark this point, and this is the most important point of this slide, that the signer never signs the actual message. You always sign the digest, and we will see in the next coming videos that you are not signing the message. Remember guys, you are signing the digest. And how you're getting a digest? You take the message, push it through the SHA function and get the output, and then you sign it, right? So, and message digests, as we already saw several use cases, they can also be used for password storage, where message digest of a password is stored instead of password itself. So you would have seen an Oracle database, like the Oracle database will never store the password itself, but it actually stores the message digest, right? Very important. So the most commonly used message digest algorithms are, we already had a look, but what is SHA? SHA stands for Secure Hash Algorithm. SHA, Secure, S, Hash, H, and Algorithm A, which includes the SHA 1, 2, 5, 6. So these are like most common and popular ones. So message digests are an important tool in cryptography for ensuring data integrity and authenticity. So I've already talked about these concepts for a lot of times. So all you're getting with message digest is your data integrity and authenticity. So with this, we actually learned what is a hashing algorithm, what is hashing, what are message digests. So thanks for watching. Okay, so it's time to take a look at another key artifact of PKI, or the public key infrastructure, which is digital signatures. Now, you must have heard a lot about digital signatures. Every time people say that I would like you to digitally sign this document, or you're using digital signature here. But what is a digital signature, right? So a digital signature is nothing but a mathematical technique which is used to verify the authenticity and integrity of the digital document or the message. Very important, right? So what it is saying is, two things are most important for digital signature. Authenticity, that you are the right person, right? If I am signing this document, then it is me who has signed the document, right? And it is not somebody else who has signed the document. So that shows authenticity. Second is integrity. What it means is that the message has not been tampered. So when the message goes from the sender to the receiver, the contents of the message hasn't changed. That is what will give you integrity. So that is what a digital signature is all about. It's a mathematical technique which used to verify the authenticity and integrity of the digital documents or messages. So as you can see here, you have a message, you are signing that with your private key. But remember, I told you, you always sign the message digest. And how do you get the message digest? You use the text or the input text, apply the function or the hashing function to get the digest. And then you sign it using your private key. Always remember, you are signing with your private key and you are verifying with the public key, right? So it is created by using a private key to encrypt a document or message and can only be decrypted by the corresponding public key. This is what we are showing here, that you are encrypting with a private key and you are decrypting with a public key. As I said, because it's all about integrity, you always encrypt not with the public key, but with the private key, because you want to ensure that you are the person who's actually sending that document and that document hasn't been tampered. It provides a way to ensure that the content of the digital document has not been tampered. And we'll take a look in a more workflow diagram. We'll show how this digital signature takes place. But all we are ensuring is that the message has not been tampered. And digital signatures are commonly used to authenticate the electronic documents, such as contracts. So whenever, let's say, you are signing a contract with your solicitors, right? They will ask you to digitally sign the document. several agreements if you're making, especially with legal and financial documents, the digital signatures are very important. Thanks for watching. Okay, so it's time to take a look at how digital signatures work under the hood, right? So till now, we got good understanding about what are digital signatures, but now in this video, we will see how you can actually make use of digital signatures in a practical situation, right? So here we are talking about two people, Joy and Aileen. Now just think about it, that Joy has to send a legal document and digitally sign, and Aileen is her solicitor. So here we are talking about a digital document, or an important legal document that has to be digitally signed and sent over to the solicitor. So let's see how it goes, right? So the first thing is, as we are talking about asymmetric encryption, as we've learned, so here you have a public-private key pair for Joy, you have public-private key pair for Aileen, although they won't come in use, but yeah, we'll see. Right, so as I told you, and what we've learned in previous lessons is that the message always passes through a hashing algorithm, right? So in this, the hashing algorithm that we are using is a SHA-256. So the message passes through a hashing algorithm, and what do you get? Any guesses? Yes, you get a message digest, or you can also call it as a checksum. So sometimes we call this as a checksum or a message digest, right? So now you got your message digest as this thing, right? And I told you that if you change hello to cello, or if you remove the H or put a say a space somewhere, you're automatically the message digest will change. Okay, all good till now? The second thing I told you guys was that whenever you are doing encryption, you always encrypt the message digest and never the message, because message is quite big. It could be a lot of pages and all, so you're not doing that. So first we create a digest and then we encrypt it, because here we are talking about digital signatures, and the most important thing in digital signature is the authenticity and integrity. What it means is that Joy is the right person who's sending it. It's not a hacker who's signing the document, the legal documents, and sending over to the solicitor, right? So it's very important that the authenticity and integrity is maintained, and that's why, any guesses? Yes, you will use, or Joy will use, his own private key or secret key to encrypt this message digest. And yes, what do we get? A digital signature. So it is as simple as that, right? So till now, you guys must have been getting confused of what is a digital signature, how it works, but this is how you get the digital signature. Now, what happens from here on? So from here on, you will take the message and you will apply this digital signature and send it over to Aileen. Now, when Aileen receives it, she needs to decrypt this. So she needs to check it internally that you are the right person, or is it actually being sent by Joy, or somebody has actually tampered it and signed as a hacker and sending it over to Aileen. So what Aileen does, because this message digest was encrypted using Joy's private key, there is only and only one key in the whole world which can decrypt it. Any guesses? Yes, it is Joy's own public key. So this is Joy's public key. Because it is publicly available, so Aileen can apply Joy's public key onto the message digest, and what does she get? She gets the message digest back, right? So that's the beauty. So now you get the message and you get the message digest, but it doesn't end here. From here, Aileen doesn't know whether the message has been tampered even now. So what Aileen will do is, Aileen will take this whole document and pass it through the SHA algorithm, right? So Aileen will pass this message through the SHA algorithm, and what does she get? She gets the message digest, right? And the good thing is, now Aileen is able to compare, oh yes, this is what I have received, and this what the message is giving me as a message digest, and both of these are equal, which indicates perfect. It indicates authenticity and integrity. That is, Joy is the right person who is sending me this message, and in integrity, because the message hasn't been tampered, I'm getting the same value of the message digest which was there in my in the message itself, right? So this is how the whole digital signature works under the hood. I hope you liked the video. Thanks for watching. Hello and welcome. So we are learning PKI, or the public key infrastructure. And one of the key pillars of the PKI is the CA, or the Certificate Authority. Now, what exactly is a Certificate Authority? So before we actually go into more details of a Certificate Authority, I normally say that it's the best diagram to actually understand how a CA works. So just think about it, that you are the applicant and here is a Certificate Authority. So when we are talking about the applicant, we can say this is something like a facebook.com, right? So when Facebook would have established, it would have come up with its own website, its domain, everything, right? And the CA here, we are talking about a big CA, something like a DigiCert, right? So let's say you are coming up, or it's a Cloud Alchemy or any of your organizations, right? So how does a server or an organization request for a CA? It's for a certificate, right? So what happens is, first of all, you need to have your identifying information. And when I say identifying information, if it is a website, you will actually give the website URL, you will give the domain name, you will give the organization name, say address of that organization. So anything that identifies you as an entity has to be sent over in a CSR. This is called a CSR, which is a certificate signing request. Now, it's very important that when you send your CSR, you need to place your public key inside this CSR, right? So you are having your, say, identity, information related to your identity, so that the certificate authority can know, okay, you are applying for it, you are facebook.com, this is your domain address, this is your organization, this is your actual address, all that stuff. And you also key in your public key. So this information then goes over to the CA, right? So it comes to the CA. Now CA, as I told you, is the top authority. So the who takes care of the actual identity information or checking the identity? It is the RA, right? So the RA will take care of your all the identities, and also it is the RA. We learned about that in the previous lesson. So RA will go and check your identities. Okay, are you facebook.com? Do you have this domain registered against you? All that stuff. When RA says that's all good, then CA can go ahead and issue the certificate. But most important thing here is that when the CA issues the certificate, it actually signs that certificate with its own private key. So please don't get confused. As an applicant, as a server, you put your public key, but when the signing is done, signing is always done with the private key. So here this certificate authority or the CA will sign using its own private key and send it over back to the applicant. So now let's take a look. So what is a CA? So a CA is nothing but a trusted third-party organization that issues digital certificates, right? So you are issuing digital certificates to individuals, organizations, devices. CAs are responsible for verifying the identity of the entity. So as I told you, if you are saying you are facebook.com, CA will actually check. So it's not the CA, but actually the RA. But anyways, it's underneath the CA, right? So it will check your identity. If you are saying you are Facebook, are you actually Facebook or not? Right. The main role of CA is to establish a trust. So this trust that is being established between whom? The client and the server, right? So that's why when you are going to facebook.com, hsbc.com, you are trusting that server. You trust hsbc.com that if I'm going to make any transactions on that, I'm pretty sure that nothing is going to the hackers. It's actually going to the databases of HSBC, right? So, but main role of CA is to ensure that this trust is built between the two parties that can share information, right? So we always say that there is a root CA. There's a concept of a root CA and intermediate CA. So the root CA is the top of the hierarchy and responsible for issuing the intermediate CAs, right? So, and intermediate CAs are the ones who actually issue the certificates. And you will always see that, we will see in an example as well, the root CAs are normally self-signed certificates, right? So root CA doesn't have to go to a signing authority to get the certificate signed. the intermediate CA has to get it signed by the root CA. So it's always remember, root CA is at the top of hierarchy and responsible for issuing intermediate CAs, which in turn issue the certificate. And root CAs are typically owned by government agencies, large corporations, like I told you, like DigiCert, Commodore. These are like some of the big names in the industry which are actually used as CAs. So intermediate CAs are owned by organizations such as commercial CAs, universities, large corporations issue certificates. So intermediate certificates come at a slightly lower level. Root CAs are more kind of big organizations, you can call it. And they are also responsible for revoking certificates that have been compromised. So there can be things that certain certificates could have been expired, they could have been hacked. So they maintain a list of that, and this is what we learned previously, the CRLs, the certificate revocation lists. So CA is responsible for revoking the certificates that have been compromised, right? So always remember that. And digital certificates issued by CA are used in various applications, such as secure web browsing. Whenever you do HTTPS, it means you are doing a secure web browser. Email encryption, the MIME concept, and the virtual private networks. So wherever we are talking about, say, a secure connectivity between client and server, you will always talk about the certificates. And I normally say that whenever we say data in transit encryption, right? Whenever we are saying that the data in transit, like when you're sending the data from client to server, that is encrypted. In that there would somewhere be a concept of certificate somewhere. And whenever there is a concept of certificates, there will always be some root CA or a certificate authority sitting on top, which would be issuing the certificates. So remember, the certificate authority is a trusted third-party organization which issues digital certificates. In next video, we will take a look at what exactly are digital certificates, and we'll do more under the hood analysis of digital certificates. Thanks for watching. Hello and welcome. So in this video, I actually want to show you the real CA, or the certificate authority, right? So I talked a lot about what are CAs, what is a certificate authority, how do you get it signed, but I really wanted that in one video I'm able to showcase a real world CA, and that is DigiCert, right? It is one of the biggest CAs in today's world. So if you read it, it says from early web CA to today's extension of digital trust, through entire ecosystem, we secure the threads and keep the real world running, right? As I told you, that it is the backbone of e-commerce, right? How you trust, say, hsbc.com or facebook.com. But if you want to actually have a look, it's a very good, say, a page that they have created which shows the entire history of DigiCert. DigiCert was not actually DigiCert. So it all started in 1995 when it was called VeriSign. So VeriSign was the very first certificate authority. And a lot of guys, if they go back to the past, they might remember this name called VeriSign, right? So in 1995, it was called VeriSign. And then DigiCert was founded based on SSL, because in 2003, they founded it as DigiCert. In 2005, they say that DigiCert became a founding member of the CA or the browser forum, right? It's all given here. Then few interesting bits come. In 2007, DigiCert partners with Microsoft to develop the industry's first multi-domain certificate. If you see, it's a multi-domain certificate that they created. And another interesting bit comes in 2010, Symmetric. Actually, you might remember Symmetric with Norton antivirus, and also Symmetric actually acquired VeriSign authentication and rebrands the iconic trust seal. So it was actually called Norton Secured, powered by DigiCert, right? If you go further down, you'll see in 2013, DigiCert became the industry's first CT log, which was actually accepted by Google. Few more changes came. 2015, DigiCert launched the scalable platform to secure IoT devices. So IoT is nothing but Internet of Things, we call it. And 2016, see how changes are happening. DigiCert introduces a digital identity for drones that are based on proven PKI standards, right? So now you can see what we are learning, PKI. So all this is getting implied here. Then 2017, actually, following the Symmetric distrust. So this distrust happened with Symmetric. DigiCert acquired Symmetric website security business and reissues all certificates on DigiCert's trusted routes. So from this point onwards, in 2017 onwards, DigiCert became the actual authority. Right. So then in 2019, DigiCert acquires Qvadis, the leading qualified trust service provider in EU and Switzerland. So they've been expanding a lot. And 2020, it was DigiCert announces the DigiCert 1, which is a holistic approach to PKI management. So why I'm showing you all this is because what we are learning, we are learning PKI, we are learning CAs, certificate authorities. And this is a real world scenario that I'm showing you in front of you. So thanks for watching. Hello and welcome. So we have talked about digital certificates quite a lot, right? So in the previous video also, we talked about the CAs, what is a certificate authority, what is an RA or registration authority, and all these CAs are actually issuing you a digital certificate, right? But what exactly is a digital certificate? So let's take a look. So a digital certificate is nothing but a digital document which is used to verify the identity of an entity or person online, right? Again, taking the example of Facebook.com. When you are going to Facebook.com, the digital certificate of that server or that web server is ensuring that it is really Facebook.com. So it's basically a digital document which is verifying the identity of the person. Now, if I take you back to the example of certificate authorities where we learned about CAs and what is a CA, I told you that it actually starts with the CSR, which is a certificate request that you raise, certificate signing request that an entity raises or a web server raises. So in that you have all the details about the identity, like if you are Facebook.com, what is your domain name, what is the URL, what is your address, all those details go in that. So that's why we say digital certificate is a digital document which verifies your identity, right? It contains the information about the owner of the certificate, such as name, address, and public key. Again, if I take you back to that example where we showed you that how a CSR travels or goes to the CA, I told you that first all the identity information goes into the CSR, and then you have to put or seed your public key inside that certificate's request. And when the CA signs with its, any guesses? Yes, the private key. So all the second point says is it contains information about the owner of the certificate, like Facebook.com, their name, their address, their domain, along with their public key. Next, the certificate is issued by a trusted third-party organization, CA, very it's self-explanatory. We already learned that there are so many CAs available in the market. The topmost I showed you is DigiCert, right? So the certificate, that request that we are sending is actually signed by a trusted third-party organization. So the CA actually verifies the identity, but it's not actually the CA, but it is actually an RA, which we call the registration authority, which will actually check whether if you are saying you are Facebook.com, it will go and check, okay, is the domain registered against you? Are you giving the right information? Do you have the right address? So it goes through a process of validation, right? As it says, it includes checking legal documents, conducting background checks, and verifying the domain ownership. So a lot of all these checks are done by the CA. Or the RA, you can say, and based on that, the CA then issues the certificate. So once the CA has verified the identity of the certificate owner, they issue the certificate and sign it with their own digital signature, indicating that it can be trusted. Now, if we talk about this line, very important, which it says is signed with its own digital signature, right? So I told you that a CA signs with its private key. So CA will always sign with its private key on the CSR that it has received, right? So digital certificates are commonly used in e-commerce, online banking, and other applications where secure communication and data transfer is important. So as we talked about it earlier, it's all about forming a trust between a client and a server, right? So we wouldn't be shopping, doing online shopping on Amazon, or we wouldn't be posting videos or our photographs, personal photographs on Facebook if we wouldn't have trusted these. So this trust, the trust that is brought by a CA or a digital certificate. So yeah, the use of digital certificates helps prevent fraud, hacking, and other types of cybercrime by ensuring that only trusted parties can access sensitive information. So it's again the same thing. Because of digital certificate, we can trust that Facebook.com is really Facebook.com, or Amazon.co.uk is actually Amazon. I can go and shop. I can give my Amex card details. I can put my credit card details without worrying about anything. So guys, very important. In this video, we had a look at what is a digital certificate. In the next video, we will actually go and check at a real world digital certificate, how digital certificates look like. I'd like to do a demo or a practical of how digital certificates look like. Thanks for watching. So in the previous videos, we saw what a digital certificate is, right? We also had a look at what is a CA or a certificate authority. We had a look what is an RA or a registration authority. So all these things we have studied. But in this video, what I want to do is I want to do a kind of under the hood digital certificate, how it actually would work in a real world scenario. So let's say I take my example here. I'm actually coming up with a new website or a new domain. You can say it is Cloud Alchemy Academy, where I'm actually creating all my courses anyways. So I, as a web server, let's say I have got my public key as well as private key. So this is my public key and this is my secret key. So if we go further, the first thing that we need to do, and we have learned so far, is we start with a certificate signing request, a CSR, right? So how does the CSR look like? So a CSR, as I told you, will have my identity, right? Two things. It will always have my identity and it will have my public key, right? So public key would be embedded in my CSR. So in terms of identity, as I said, it will be all the details. What is my website URL? What is the domain? Where am I registered? All this stuff. So if you see, name is cloudalchemy.uk, organization, let's say Cloud Alchemy Limited, and the country is UK, right? Now, this CSR has to go to a certificate authority, something like a DigiCert, right? So you can just imagine in terms of, okay, there are intermediate CAs and there is root CA, but to generalize it, I would say it will actually go to a certificate authority. And the first thing that a CA or an RA would do is scrutiny. They would check, just like a detective, as you can see here, they would actually check whether I am really cloudalchemy.uk or I'm some hacker who's trying to pretend to be a cloudalchemy.uk, right? So they will be checking my identity and they will be looking at this CSR. And once they are happy with this whole thing, they would say, okay, yes, I can stamp it, and they will stamp it with their or encrypt it with their private key. So the CA will encrypt or place its private key to generate a digital certificate. So this is how a digital certificate of Cloud Alchemy UK would look like. So whenever a client sends a request to the Cloud Alchemy UK, this is the certificate that would be passed back to the client, right? So always remember, when you're doing facebook.com, you're doing amazon.co.uk, on your web browser, you send a request to the web server and the web server actually sends the certificate back. So another key important thing always to remember, people tell you that in the TLS handshake, or when this handshake takes place between client and server, the server sends the public key. No, the server never sends the public key. The server always sends the digital certificate. Always remember, the server will always send you the digital certificate, never sends the public key. So this is how your certificate looks like under the hood. I think by now you've got a very, very good understanding of what a digital certificate is, what is a CA, what is a root CA, how this whole thing of getting the stamp or getting the authorities from CAs works in the real world. So thanks for watching, guys. Welcome to an interesting demo on digital certificates. Here we will actually do a scrutiny of a real world certificate, right? So how does it work? So let's take a look. So if you go to facebook.com, you will always see that there is a padlock. If you are getting a padlock, it means that you are on HTTPS. Or you can say it is a secure communication that is going to happen. So if you click on this, you will see, and then I'll actually read out for you because it's very important. Whatever we have learned so far, we are going to apply the same knowledge. So it says Safari is using an encrypted connection to facebook.com. Good. So it means that you can trust this connection or this server itself. It says encryption with digital certificate. So there are two things. You are using encryption, what we have already learned. You are using digital certificates, which we have learned as well. We'll keep the information private as it's sent to and from the website. So what it means is that whatever communication is happening between the client and the server, there is no man in the middle coming here. It's all encrypted connection, right? So you can just go ahead, you can post your videos, you can post your photographs, or if you are on amazon.co.uk, you can easily go and do your shopping. But let's take a look at this certificate, how this certificate looks like. Amazing. So this is how the certificate looks like. Okay, so let's take a look. So first of all, we need to understand this bit. The first bit is that facebook.com certificate has been signed by DigiCert SHA-2 High Assurance Server CA, which is an intermediate CA. So if you see here, it says intermediate CA. And then this certificate has been signed by DigiCert, the one that we looked at. And this is the root CA. If you see, it says root certificate authority. Perfect. So now this is what we talked about: root CA, intermediate CA, and the actual requester. So Facebook is the requester. This goes to intermediate CA, which would have taken a look at Facebook's identity, the domain name, whatever information they gave. And then when a green signal was given, the root CA signed it. And always remember, root CA always signs its own certificate. It has got that authority. So if we look at facebook.com, if we start looking at the details, so what are the contents of it? Let's take a look. The first thing is, as I said, the first thing is always the identity, what it is. So it will tell about, okay, country or region is US, county is California, locality is Menlo Park, organization is Meta Platforms, and common name is facebook.com. So this is all the information that facebook.com would have given, and much more, to prove its identity, that yes, I am facebook.com, right? Then it gives the details of the issuer name. Issuer name, if you understand, is the intermediate CA. So the intermediate CA here is DigiCert SHA-2 High Assurance Server CA. Now the details of that, it shows issuer name, country origin is US, organization is DigiCert, we already had a look, organization unit is digicert.com, I already showed you the website of that. So the common name that you use is this one, the serial number, like you can say a unique number is this, the version is this. And guys, just have a look. What kind of encryption are they using, and the signature algorithm they are using? SHA-256 with RSA encryption. Everything that we have learned so far, everything we learned about these hashing algorithms, we learned about in-depth RSA encryption. So everything is in front of you. Now it would become so easy. Then I also told you that every CA or every certificate would have some public key information as well. And just have a look at the algorithms they are using. Elliptical curve public key, elliptical curve security key. Then you have the public key details. If I click on this, you'll see that the entire public key, the key size, the key usage, signature. So whatever we learned, we learned all these. So this is all in front of you now. And rest are more about extensions. You can actually go about and read about it. So again, if I go up and try and see the details of who's the signing authority, who's the intermediate CA here, it is the SHA-2 assurance. And here again, just the details about it. And important thing is that this certificate for SHA-2 has actually been signed by the root CA. So if you see, The common name is DigiCert High Assurance Root CA as part of the issuer, and rest of the details are same, like signature algorithm, SHA-256 with RSA, and all this rest of the information. Now, if we actually take a look at root CA, it's very interesting because I told you that root CA is self-signed. So root CA doesn't have to go to any certificate authority to get the signature. It is always self-signed. So if you see, the subject name is also DigiCert. The common name is DigiCert High Assurance EV Root CA. And who is the issuer? If you look at the root CA, common name is same, DigiCert High Assurance EV Root CA. So it means this is a self-signed certificate, but it is only the root CA which can have self-signed certificate. Because if you again quickly take a look, if you look at the issuers for intermediate CA, you will see the common name was intermediate CA's name and the issuer name was DigiCert Root CA, right? And for Facebook.com, it was the issuer. So if you see, common name was Facebook.com and the issuer name was Higher Assurance, right? So this is the kind of hierarchy it follows. And so I think with this video, you will have got a very, very good understanding of what is a digital certificate, how it really looks like, because when we are working on all these things, we never imagined that it's so easy to look at and do a scrutiny of a digital certificate. So with this video, we did that. I hope you liked the video. Thanks for watching. Okay, so another interesting video is coming your way, guys. So here we will try and understand the benefits of a digital certificate, or just try and understand the architecture, how a digital certificate is architected, and how it actually prevents a man-in-the-middle attack, right? So let's take a look. So here I'm talking about, let's say you have a digital certificate, or there is a company called HSBC, it's a bank in the UK. So let's say they have actually created a digital certificate. They've gone to the CA, and the CA has actually certified the digital certificate with its own, say, private key, right? So how it goes is that you have, say, as we said, that every digital certificate would have its own identities, right? So, and you will always embed your primary key and your public key in it, right? So all we are saying is you have an organization, hsbc.co.uk, and its organization is HSBC and the country is UK, and this is the digital certificate, and this is your, let's say, the secret key, because it was signed by the CA, right? Now, as a client, what you are doing is you are requesting access to the website. Let's say you are saying you are sitting on your web browser, and from your web browser, you are requesting hsbc.co.uk. So what a server does, as I told you, that a server never sends the public key back. The server always sends its digital certificate, right? So what HSBC would do, HSBC's web server will actually send its certificate back to the client, right? Now what happens? Let's say there is a smart hacker sitting somewhere in Russia, and that hacker thinks, okay, let me grab this certificate, let me create my own certificate and send it back to the client, so that I start imitating like hsbc.co.uk, right? So what that guy will do, it'll just create a fake certificate. So again, that smart hacker is having his own public key and secret key, or the private key. And if you see, the smart hacker will actually just imitate this certificate and create its own certificate. Something like a name is darkweb.com, organization HCC, country Russia, and it will just try and send this certificate back to the client who was actually requesting this certificate, right? So now you might think, okay, the request has gone to hsbc.co.uk. In between, there is a man in the middle sitting somewhere who's taken that certificate which was coming back, made some changes in that, and sending this back to the client, because the client still thinks that I'm talking to hsbc.com or hsbc.co.uk, but this man in the middle now grabs this certificate, changes it, and sends it back. Now, what do you think happens? You might think, because I'm talking to hsbc.co.uk, and if the man in the middle is changing that certificate, sending it back to me, so I won't come to know. No, it doesn't happen like that. So this actually certificate comes and gets processed by the web browser. So you will have, let's say, Google Chrome, you will have Safari, and you'll notice that all our web browsers always store some certificates as well. And the other important thing is that why this certificate would not work is because, as I told you, that the CA or the certificate authority uses its or signs, encrypts it with its own secret key. So which is the key in the whole world which can decrypt it? So you need to use the CA's public key. Now these web browsers are intelligent. They already know about all these the CAs and the CA's public key. So the web browser tries to use the CA's public key, and hey, there is a mismatch, right? Why? Because it's not able to decrypt this certificate in that sense, because it has been used or it has been encrypted by some other private key. By this, it comes to know, hey, so there is a man in the middle, and what it will do, it will very intelligently say invalid server certificate, and it sends a request back to the client saying, no, I can't open this web page, which darkweb.com that is sending me, because it is an invalid certificate. I need the certificate which has been sent by or signed by the CA, the trusted authority, because the whole concept is trust, right? This whole thing is based on trust. If you're not able to build that trust between the web browser and the web server, then it means the communication, the secure communication, can't take place. So that is why this video was so important, because we wanted to showcase what is the benefit of digital certificate, how they are created, how they are organized, and how even a man in the middle can't do anything with these. So in the next video, we will actually take a look at what are self-signed certificates. Thanks for watching. Hello and welcome. In this video, we will talk about the self-signed certificates. So this is more of a theory for self-signed certificates, but we did actually take a look at self-signed certificates, if you might remember, when I was actually showing you the certificates of facebook.com. So when we did when we checked the certificates, so you had the lower say level was facebook.com, then on top of it you had the intermediate CA, and then at the top level was the top CA, or we call the root CA. And I told you that the facebook.com will get its certificate signed by intermediate CA, and the intermediate CA then in turn gets its certificate signed by the root CA. And always remember that root CA, there is no issuer on top of a root CA. So root CA can actually self-sign its own certificate. But sometimes these self-signed certificates can also be utilized. So let's take a look. So a self-signed certificate is nothing but a digital certificate that is created and signed by the same entity. Very important that you are actually signing, so you're not actually going to any issuer, or you're not going to a CA to get your certificate signed, rather than being signed by a third party CA, right? So very important that you are the person, let's say if I am creating a certificate, I'm signing it myself. That is what we call the self-signed certificate. So which means I'm not actually going to a trusted CA or a certificate authority or a third party trusted CA to get the certificate signed. Now you might ask, why would I do that? Yes, normally people do that when they are building development environments, right? Quite important, when you are building dev environments, you don't want to spend too much on getting these signed certificates, because they are expensive, right? So we say that normally in testing and development environments, also sometimes in small scale deployments, it may be practical to actually just use a self-signed certificate and not go for a trusted CA. Right. So, but self-signed certificates are not considered as secure. Please remember, they are not secure. The only secure way to get a digital certificate is through trusted CAs. right? Because why? Because they don't have the same level of validation, right? Because we told you that whenever you request for a certificate to the CA, it has to go through a proper scrutiny, right? You might remember the guy with the lens was checking it. So what it is doing, it is actually this trusted organization is actually checking for your identity, right? So that's why if you are using a self-signed certificate, we don't consider it very secure. And there are actually a lot of tools available, and we will see in a demo as well how to create a self-signed certificate. So self-signed certificates can be created using tools like OpenSSL, very popular tool in the market, and we will use that to showcase in a demo as well. So you can use OpenSSL to create your self-signed certificates. Very important. The browsers I told you are very intelligent these days. They are always looking for certificates, right? Trusted certificates. So whenever you use a self-signed certificate, your browser will always display a warning. It will indicate that the certificate you're using is not trusted. Do you really want to use it? And you have to accept it. So you manually accept the certificate in order to proceed, right? It is possible for attackers to create fraudulent self-signed certificates, which can be used to conduct man-in-the-middle attacks. So we showed you the HSBC example, right? In that example, if you remember, I took hsbc.co.uk certificate and I used say the hacker came in and changed it. Just imagine if that certificate was a self-signed certificate. Then what would have happened, right? So what would have happened is anybody would have changed it and it would have been sent to the client, and obviously the browser wouldn't have come to know, right? Because using a self-signed certificate, and that's why the browser always gives you a warning message. So always remember, these self-signed certificates are always prone to these attacks from the hackers, right? And self-signed certificates normally have expiration dates, so they do expire after a while. So, and you need to renew it periodically to maintain it valid. But it's quite important, right? Because they are not very secure. So you use it for only for temporary time or temporary purposes, and then they expire. So they shouldn't be actually used after that. So very important. And what a self-signed certificate is. So in the next demo, I will actually show you how you can use or create your self-signed certificate. Thanks for watching. Okay, so before we actually jump into the demos, I thought it would be quite important if we actually discuss a couple of file formats which are very important for you guys. These are PEM and PKCS12. So now the certificates that we are creating, or the digital certificates that we are creating, can either be stored in a PEM or in a PKCS12 format. So what exactly are these? Let's take a look. So PEM or PEM stands for Privacy Enhanced Mail. It is a base 64 encoded file format, right? So what does it mean? So a base 64 encoded file format represents the binary data into ASCII string. Now, very important that a PEM format is used to store digital certificates. You can store your private keys, and you can even store other types of data such as the certificate revocation list. Now, what was the CRLs? I told you that there are certain certificates that have expired or can't be used. So the trusted CA will always create this kind of list, which is called a certificate revocation list. Okay, now very important, another format is PKCS12. A lot of people don't even know the full form of PKCS and what it is. So PKCS stands for Public Key Cryptography Standards. PKCS, Public Key Cryptography Standards. And it is a binary file format. So very important, this was encoded, base 64 encoded file format, and this is a binary file format. And this is actually used to store digital certificates and private keys. Only two things. Always remember, PKCS is storing digital certificates and private keys, but it can be in a password protected file, right? Always remember that. So you are storing, it is a binary file format which is used to store digital certificates and private keys in a password protected file. Very important. Now, if the guys who would have worked on Oracle or when they're working on TDE, when they are storing their master encryption key, they always store it in a wallet, and this wallet is actually password protected. So they are using a PKCS kind of format, right? So PKCS 12 files can also include additional files such as intermediate certificates and CA certificates. Okay. So now sometimes people ask, what are the key differences? I'm still getting confused. They say, what is the key difference between a PEM and a PKCS? So the very first difference is the encoding scheme, how the data is stored. So PEM files are base 64 encoded text file, whereas PKCS are binary files. Very key important difference. Then, as I told you, PKCS 12 files can be password protected, right? And PEM files are not. So you can't password protect your PEM files, but you can password protect your PKCS 12 files, right? However, some software applications that use PEM files may require a password to protect the private key. File content. Now, again, I told you that what can be stored in a PEM format or what can be stored in a PKCS 12 files. So PEM files can contain different types of data. You can have certificates, you can have private keys, you can have CRLs, but PKCS has only two types, digital certificates and private keys. Always remember, PKCS 12 has only two things, digital certificates and the private keys, right? Platform support. Again, now different types of formats are actually available on different kinds of platforms. So PEM files are commonly used. I'm using a term here, commonly, right? So it is available, but commonly used in Unix systems, and PKCS 12 are widely used in Windows-based systems. So wherever you will see a Windows-based system, you will always see, you will have PKCS 12 kind of files. And whenever you are working on Linux systems, Unix systems, you will always see that there will be PEM files. So these are the PEM files where you would be storing your digital certificates. So now I have another video after this, which will talk about the chain of trust. What is a chain of trust? It's just a kind of theory that you guys need to know what this term chain of trust means. We've already studied that in a demo I did earlier when we were talking about Facebook, but I just want to show you that, okay, what is a chain of trust? And then we'll actually move on to demos, interesting demos where we'll use OpenSSL to generate our certificate signing request. We will sign those certificates. So all this stuff will work on. So thanks for watching, guys. Okay, so in this video, we will talk about what is a chain of trust. So although, again, we already had a look at this when we studied the Facebook.com certificates. I showed you that Facebook.com was getting its request or the certificate signed by the intermediate CA, and the intermediate CA was getting its request signed by the root CA. So this is how a chain of trust is formed. And whenever anybody in your organization is talking about the chain of trust, now you can easily imagine that this is the kind of chain of trust we are actually talking about, right? So let's take a look. So what is a chain of trust? So chain of trust is actually nothing but, I would say it's a sequence of events or interactions in which a trust is established and maintained between different entities. So as you can see, this is let's say the organization, it is requesting a certificate from the intermediate CA, and the intermediate CA is then requesting from the top CA or the root CA. So it's a sequence of events. Chain, as you know, a chain is being formed. So how do you form a chain? You join certain things, right? So this is how we say a chain is being formed. So a sequence of events or interactions in which a trust is established. The process of verifying the authenticity and integrity of digital certificates or public keys used for secure communication. It's self-explanatory, I'd say. I won't go into more details of that, because as you understand that as an organization, you are applying for the digital certificate, and the RA or the CA is actually checking that, are you an authentic person? Are you the real Facebook.com? Are you the real cloudalchemy.com, right? So it ensures that the authenticity and integrity is maintained. The chain of trust is established by a hierarchy of CAs who issue and validate certificates for digital signatures. Very self-explanatory again. So what is the hierarchy of CAs? We have the intermediate CA, and then we have the root CA. The top level CA is called the root CA, is responsible for issuing and signing its own certificate. Now, we already discussed that previously, that root CA is the only CA that can issue a self-signed certificate, because there is no issuer on top of a root CA, right? So each intermediate CA is authorized by the root CA. So always remember that you can't just simply go and simply go to the intermediate CA. The root CA has delegated it to the intermediate CA. So the root CA has given the authority to the intermediate CA that yes, please go ahead, check this, the identity of that person and go ahead and issue the certificate for that, right? So an intermediate CA is authorized by the root CA to issue certificates. The trustworthiness of chain of trust depends on the security and reliability of root CA and its subordinate CAs. So what it says is how this whole trust is formed is due to the security and reliability of root CA, how robust security mechanisms they are having, what kind of encryption algorithms they are using. So it's very important for the trustworthiness of the chain of trust. And any compromise or breach of security in the chain of trust can disrupt the chain of trust. So if anybody goes and hacks this into the intermediate CA, changes some information here or changes some information here, it will actually break the chain of trust. So the web browser can easily come to know that yes, somebody has gone in and changed something, and this is where they will say that it's an invalid certificate, right? So it's very important that this chain of trust is maintained all throughout the communication between the client and the server. So from now, we'll start doing some nice demos. I know you guys have been waiting for these demos, but it's right time now. So I would always advise that you can just simply go ahead and work with me when I'm doing the demos. You can do it on your systems as well, and it will be quite good for you as well. So thanks for watching. Finally come to start working and looking into the demo for digital certificates. Now, what we will use here is we will be using OpenSSL, right? So we'll use OpenSSL to create our certificates or create signing requests, and then we will sign those certificates. So we'll do it all what we have learned so far, but it would be done in a demo. So let's get started. Okay, and I would advise that you can start working with me when I'm actually working on it. So you can just start working on it. Okay, so first thing says create a new directory. So we have to create a new directory called certificates. So let's say we create a certificates directory. We go into that certificates directory. Okay, so I am in certificates directory now, right? So what it says next is I need to create a private key and a digital certificate, right? So what we will do is we'll just simply copy this and paste this. So you can do the same thing. But what we'll do is we'll go one by one. Let's take a look how it is done. So I'm saying OpenSSL is the command. We are generating a request. Now this is as we studied the X509, X508 formats. So these are the digital certificate formats we are going to use. This would be my algorithm, which is the signature algorithm that I'll be using, which is SHA-256. Here I'm saying I need to create a new key. And when obviously when you are creating a new private key, you need to tell which algorithm you need to use. So I'm saying, okay, I need to use an RSA algorithm, and the key bits I'm keeping is 2048 bits. It says for how long you want to keep it. I'll say it expires after 65 days. The key out, I say CA private.pem, which means that this would be my CA's private key. So here I'm creating a root certificate. So this is my CA's private key, and the output is a cscert.pem. That's why we learned all these formats, the PEM format, the PKCS format. So I told you that if you're on Unix systems or Linux systems, you'd be using a PEM. Here I'm on a Mac system. If you're doing it on Windows, it could be slightly different, but these things actually still work, right? So the thing is that you can say -out ca_cert.pem. This will be the certificate that would be created. So if I hit enter, it actually asks me to enter the passphrase. So why is it asking me the passphrase? Because it's a private key you are creating. So it says it's always good to protect your private key. So you're protecting your private key with a passphrase. So here the passphrase is Udemy. I'll give the passphrase Udemy. It says, okay, please verify it again so that I haven't entered something else. Okay, and then it starts asking me the information. So as we studied the identity information, who are you? So you are creating the certificate, but who are you? Okay, so it says country name. I say country name is say UK. The state or province name, I'll say England. You can change it as per what you want to give. So city, I say London. Organization name, I say MyCA. So this is MyCA. So I'm saying this is my organizational unit. Okay, so it says which organization unit are you creating the certificate for? I'll say, okay, I'm creating this for cybersecurity because this is MyCA and I should be able to sign it. And it says, okay, common name or the fully qualified domain name. I'll say, okay, it is myca.com. Right, it asks for the email address. I'll say root@myca.com. Right, perfect. So here you'll see it creates two things. One is the ca_private.pem and the ca_cert.pem. This is my private key and this is my certificate. So if I actually try and try to read it, okay, so as I told you, it is in base 64 format. So this is in encrypted format. You can't understand anything, right? Or if I see the certificate, if I try to see the certificate also comes in this format. It shows begin certificate, end certificate. Now, if you really want to see the contents of certificate, there is definitely a way, and I'll show you that. So the way to do that is we simply use the same OpenSSL command and try and give the request. So we're saying OpenSSL x509 -in. -in is I'm giving the input as my certificate and I'm saying, hey, hey OpenSSL, can you please show me the certificate in a text format? So if you see no output, but -text. Perfect. So here I can now read the contents of my certificate. This is a certificate that I've just created. So it shows certificate, data, version, signature algorithm. Very important. You might remember I said we are using SHA-256 with RSA encryption. Issuer, just have a look. The things that I entered at that time, I said UK, England, London, MyCA, cybersecurity. Everything what I entered is here. Even validity is there based on the 65 days I gave. So you can say it can be used from this period to this period, right? And then you have the other information, right? Okay, my public key, the public key bits, how much was they, and the signature algorithm, which is SHA-256 encryption. Perfect. So this is what I wanted to show you, that how a CA or a root CA can generate their own say private key and generate the digital certificate. Now in the next video, what we'll do is we will you can consider yourself like a web server, right? You are, let's say, working on a project and you want to create a certificate signing request first of all, right? So you'll create a certificate and it will be a certificate signing request which will actually go to the CA to get it signed. So we'll go step by step. So in the next video we will move and start creating a web server certificate request. Thanks for watching. Okay, so another interesting demo is coming your way now. So in the previous demo, we saw how you can create, or how a CA would create its own private key and also the certificate, the digital certificate or the root CA certificate. In this demo, we will see how, if you are, let's say, coming up with a new application and you are setting up your new web server and you want a new certificate to be created for your web server, how you would do that. The good thing is that what we learned in the previous demo is the same what we are going to apply here as well, right? So if you see, if I actually have to create this certificate, I'll just simply say the same command, OpenSSL request SHA-256. So the only difference now is that when you were doing that root CA, you were giving OpenSSL and X509, right? So here when we are doing it, we are saying OpenSSL request minus SHA-256. So there is actually a difference in the commands, right? So please don't get confused. If I actually go back to, yeah. So if you say here we said OpenSSL request X509 and we gave the algorithm. So what are we doing here? We are saying OpenSSL request SHA-256 new key. Again, the same way we are saying we need to create a new private key and we are giving the algorithm that it should be RSA with the key length of 2048. The key output is web server underscore private. So as I said, we are creating a web server private key. So web server underscore private dot pem, and minus output is the certificate itself. And again, to protect the private key, it has to be protected by a password. So here I give you demi web, and again I give you demi web. Okay, so it asks for the country name. I say UK. It says what is the state or province. I say England. Same way. It says locality. I say London. Organization name. Okay, so here in organization name I'll say Cloud Alchemy, because I'm generating it for Cloud Alchemy. Organization unit, you can say I'm doing it for tutorials, right? Common name or the fully qualified name, I can give my website name, like is cloudalchemy.uk. And email address, I can give kvjoy@cloudalchemy.uk. And it says, okay, can you enter the extra attributes to be sent to the certificate request? Here I say CCUR1TY. Okay, and this is the one that is created. So here now we have the web server private key and we have the web server certificate. Okay, so this is our certificate request that has been created, which is web server underscore cert underscore request dot pem, and the command that we will use to check the contents is different from the previous one that we learned. So it is OpenSSL request minus text minus no out minus verify minus in, and you give the actual name of the digital certificate. And here you go. So here you can see the certificate request. This is a certificate request, guys. There is a difference, right? So this is a CSR that we have created. So we will actually digitally sign this, or it will be signed further by the CA to get the right digital certificate, right? So here rest of the things are quite same what we had input, like it is England, London, Cloud Alchemy, tutorials, and rest of the information is similar, like you have the public key, you have all the attributes and whatever information we have kept, and also the algorithms like SHA and RSA encryption. So with this we come to the end of the video. In next video we will see how you can actually sign this request. So this is a CSR. This CSR will now go to the CA, or the certificate authority, and the certificate authority will sign this request. Thanks for watching. Hi folks, welcome back. So time has finally come where we will take a CSR, or the certificate signing request, and we will act as a CA itself and sign that certificate. And I'll show you how this can be done. So just as a flashback, so this was the CA private key that we had created. This is the CA cert, or the CA certificate, digital certificate that we had created. So normally they would be different. So they would have different locations, because CA would be somewhere different and your location would be somewhere different. It's just for the demo purposes. We have just kept one directory and kept everything here, just for the ease of use. And this is the web server private key that you created, and this is the web server certificate that gets generated. It is actually the certificate request. Always remember that. So let's take a look how you can actually sign this certificate. So to sign this certificate, the command that we have to use is, we will say OpenSSL X509. So remember, X509 is always used when you are creating either a self-signed certificate or you are actually signing a certificate. Then we will use X509, right? So here we are saying OpenSSL X509 minus request minus in. What are we giving the input? We are giving the input as a certificate signing request, the CSR that we generated. And then on top of it, I always told you, on the previous demos, I told you that the CA signs the digital certificate using its own, any guesses? Yes, its own private key. So here you have to give the private key which the CA will sign with. So that's why we are saying minus CA underscore cert.pem, which is CA underscore cert.pem, which is the CA itself, the certificate itself, or the root certificate itself, and the CA key, which is the CA private key, the CA underscore private dot pem. And when we are creating it, we are just saying that please create a unique serial number as well for this, and the output should be a web server underscore cert dot pem. So just notice what I'm doing. I will create a certificate that will be called web server underscore cert dot pem. So I'm just requesting removing this RAQ or the request out of it, right? So let's see how it goes. So it says, okay, signature is okay. Subject is UK, England, London, Cloud Alchemy. So it means it is going to sign my CSR. So you remember when I had created the CSR, I had created with Cloud Alchemy and tutorials. Now it says enter the passphrase for the CA.pem. So you might remember we had given this as Udemy, right? So we just give it, it is that quick. So it is already signed as well. So if you see, it has generated this web server underscore cert.pem. Now, if again, I try to check this, you will see that it gives begin certificate, end certificate, which is in the base 64 format. We can't see anything. And another important thing to notice, it actually generates a unique serial number as well. So if you see that this file gets generated, this is a unique serial number. And to actually see the contents, which are very interesting, we will actually use this command, which is again OpenSSL of X509. So we will say OpenSSL X509 minus in web server underscore cert.pem, which is the new certificate that has been created in text format. Perfect. So just have a look what we are getting now. So here you can see this is my signed certificate, right? So if you see this has actually been signed by my CA. Perfect, right? Can you see this? So this is my certificate. This is the signature algorithm. The issuer, who is the issuer? The issuer is my CA. And who is it about? It is about Cloud Alchemy. If you see Cloud Alchemy tutorials, this was the request which has been, if we go on top, signed by the issuer, which is London, England, London, and myca.com, right? Rest, it's all public key information and the signature algorithm. So guys, this is also showing you this the chain of trust that we talked about, right? So quite important demo, I would say. You should always go and do it on your PC, on your laptop. It would be really amazing to go through these certificates and get real understanding of whatever we have learned. We've actually implemented those in demos. Thanks for watching.